Good morning and welcome back to the second day of the Alternative Analysis Workshop on Lifecycle Impacts and Exposure Assessment. It's great to see all of you back again. I don't know about you, but yesterday I was having flashbacks to being in college. Now this isn't quite Campbell Hall at UCSB, and being a UCSB alumni, it was fun to kind of put myself back into those classroom shoes a little bit. So thank you, and we're all looking forward to today, I'm sure. Without further ado, I think we're ready to get started. So Sengwon Soo, Dr. Sengwon Soo is starting out the morning. So come on down. Oh, yes. Still turned on.
Great.
There you go.
Good morning, everyone. So today we will do some hands-on exercises, and we will learn a few new things from yesterday. Let's see. Here we go. So we'll just minimize this for now. That's okay? All right. So the two hands-on exercises for the first session in the morning is they are life cycle inventory calculation. And Carrie mentioned that going back to the campus, and today we will show you some equations, and I hope that you're comfortable with that. And we'll do some Excel spreadsheet exercise. But before we go into the Excel exercise, I will give you a little bit of the methodology discussion so that we can use this methodology for our Excel exercise. So first, life cycle inventory calculation. So yesterday we learned about life cycle inventory, which is about calculating the amount of elementary flows going in or coming out of our system throughout the life cycle. That's what life cycle inventory is about. We are recording the elementary flows. We are targeting the elementary flows that is coming from the nature or going out to the nature without prior or further the subsequent human transformation. We will actually do simplified life cycle inventory calculation for these two chemicals that we have gone through yesterday, methylene chloride and benzene, used widely for paint stripping. And these are the processes and these are the inputs needed for methylene chloride and the benzene. Yesterday we talked about kind of tree-like structure. Tree trunk is the final product, and then all the branches are the intermediate inputs needed to produce them. And the elementary flows are going in and out throughout the upstream processes. And that's basically how life cycle inventory problem is formulated generally. So then the question is, how do we represent unit process in life cycle inventory problem solving? So inputs and unit process is basically the basic elementary unit that records inputs and outputs, such as, for example, in the previous case, okay. So if I can go back, going back doesn't seem to work. Yeah, great, thank you. So each of these boxes can be the unit process. So producing chlorine, for example, what are the inputs and what are the outputs? Intermediate inputs means the inputs from other processes, and elementary inputs and or outputs means the inputs from nature or outputs to the nature. So how do we record that? How do we represent that? So we generally represent them as a vector. So intermediate processes, you can imagine that the process one inputs are recorded as numbers from other unit processes. So A11 we will show the amount of input from process 1 to process 1, and amount of input from process 2 to process 1, and amount of input from process 3 to process 1, etc. Yeah? And for the process 2, we can do the same thing, and process 3, we can do the same thing. If we do that and we stack up together, probably I would prefer this amount. No worries. If we stack up, then we generate a matrix like this, and we call this as a technology matrix. So this technology matrix basically shows the inputs and output structure from other processes. These are the interactions amongst the processes. It does not involve any elementary flows. So it involves only the intermediate flows amongst those processes, right? And this is, in our calculation, it is, I wouldn't say always, but it should be generally square, meaning that, well, the number of processes that are giving or receiving inputs are the same as the number of processes that are giving or receiving outputs to other processes. Yep. So we will show you the actual example later on. I will actually skip this. We have very tight schedule, so we will actually just run into the matrix algorithm to calculate this. So it looks like this. So for the methylene chloride, I think this is a methylene chloride example. In order to produce 1 unit of methylene chloride, you see over here, top left, producing 1 unit of methylene chloride requires consuming 0.6 kilograms of chloroethane. And it seems that it needs 0.82 kilograms of chlorine gas. And it does not need the hydrochloric acid, etc. And then it does need water, natural gas, and electricity of these amounts. No? Yes?
Is there any public database where you can obtain those information for unit chemicals?
Yes. So yesterday, you remember that almost at the last minute, I showed you a whole bunch of links on lifecycle inventory databases, such as US Lifecycle Inventory and EcoInvent databases. They basically have this kind of information. However, these databases are not complete. So as we will go into the examples later on, when we talk about proxy values, we may not actually have the particular chemical of interest that we want to run the analysis. In that case, we may need to rely on proxy values. So EcoInvent database contains about several hundred chemicals. And our Click tool, which we will show you later, it has about 1,200 chemicals, and we also allows you to use the proxy values based on the chemical structure similarities. Okay. That's a good question. And then the second column is about the second flow, second row. So it produces chloroethane. Therefore, the diagonal, so the second row should be 1, meaning that it produces 1 unit of itself and consumes other inputs. And if we do that for all the processes that we need to complete the life cycle, inputs for producing methylene chloride, you can see, well, this is a whole matrix. In reality, however, producing one chemical may involve hundreds of unit processes throughout the upstream. If you can imagine that it requires, let's say, coal, and coal requires machinery, and machinery requires steel, steel requires, another coal, and electricity, and these kind of process interactions propagate throughout the upstream quite expansively. So it may actually reach out to the global economy. So these are very simplified examples. Generally, when you look at the EcoInvent processes, it involves actually all processes within the database, which contains 11,000 processes. Any single chemical, any single product in the EcoInvent process requires inputs from all the rest of the processes, 11,000 processes. Even so, it is a simplified version of reality. So in any case, if we do that, you can imagine the diagonal should be all 1, right? Because we want to produce each of that. And as you can notice here, consumption is using negative value, while production is using positive value. Why this is useful? Because as we will see, this is in a sense a balancing equation. This forms a balancing equation using of which we can actually generate lifecycle inventory, use of which will generate the lifecycle inventory. What we also need is what is called reference flow vector, which is showing 1 for the target chemical of interest, in which case methylene chloride. So methylene chloride is turned on as 1 over here, top, and then all the rest is 0. And we also need the environmental matrix. These are the elementary flows. So again, the technology matrix, or A matrix we sometimes call, is about intermediate flows, and environmental matrices are about elementary flows. And these are the emissions directly to the nature, or resources extracted directly from the nature. So each processes generate this much of environmental emissions. And then once these matrices are all set, what we do is this simple equation. So the balancing equation looks like this. So let's say this A matrix, the technology matrix, times the level of activity of each process. If you multiply these two, it should generate the net output of our interest. What does that mean here is if we go back here, basically, suppose that this process will run X number of hours, to produce so many kilograms of this methylene chloride. And in order to do that, it requires the second process to run 0.6 times of this, right? So there will be certain number of hours that this process need to perform in order to generate that amount. And also the third process is needed for this amount. So you can imagine that there's a certain level of activity needed for each of those processes. And then each of those processes also require other processes to operate and generate their inputs, right? So all those life cycle process-to-process interactions require all these processes to be in operation to a certain level. And that level should equate production of the reference flows. All the rest of the flows all need to be consumed up by the life cycle. What we all need in the end is only this. What is escaping from this whole system is a kilogram of methylene chloride. All the rest should have been consumed by other processes to produce 1 kilogram of methylene chloride. So net output of the process, this entire system, is 1 kilogram of methylene chloride. And that is what is shown here. So what this equation is saying is that, well, you produce all those chemicals and give me the net output of 1 kilogram of methylene chloride. Yes?
So explain to me, maybe I missed something, but you mentioned that the only output would be the chemical, but we know that there's all these other outputs,
exactly. Right? All the other outputs are used up by other processes, and they are used up in order to produce all the way to 1 kilogram of methylene chloride.
So what do you do with emissions of other chemicals?
Well, so those are in the B matrix. Okay. So B matrix, as I will show you later, the environmental emissions, elementary flows are not accounted here. So what this shows is that what we are basically interested in how much of each chemicals need to be produced in order to meet the final requirements of net output of 1 kilogram of methylene chloride. And using that one, we will calculate the environmental emissions, elementary flows. So this is all about the intermediate flows. It might be actually more intuitive when we enter into actual exercise. Okay. So again, what we just have to remember here is that, well, this is a balancing equation that shows the net output of the system, which is the chemical of interest that we want to calculate life cycle inventory for. In the matrix calculations, what we do, if we're interested in understanding X, we basically multiply the inverse matrix of A on both sides so that A is canceled out into identity matrix, and basically X is calculated as A inverse times Y. So X, again, is the amount of outputs by each process is needed to produce 1 unit of methylene chloride is calculated in this way, which we will do later. Okay, and then what we have to do is, well, then we know how much of emissions are generated to produce 1 unit of each, right? So if we multiply this B matrix to this X here, then we will be able to generate the total amount of emissions needed for producing 1 kilogram methylene chloride throughout this life cycle. This is the kind of logic behind this calculation. I know that, well, it's been a while since you have been doing the linear algebra. So I understand what does the silence mean. But don't worry. As we go through the exercise, I think it may become even clearer. And if there is any question, then I will be happy to answer them. So why don't I, yes. Yeah, let's go into the Excel spreadsheet, and I would like to actually use the keyboard. Okay. So in the meantime, please open up the Excel spreadsheet, please. Yeah. Which one? So it's LCA size. So what is the name of that title? Thank you. Thank you. Great, thank you. Okay, so I hope that the folks joining us through the webcast can also see the screen, okay? Is it okay for me? Probably I want to use this side, if that's okay. Oh, it's okay, it's okay. I can just, yeah, that would be great. By the way, Munya will walk around, and if you need any help, she will be able to help you to navigate through this spreadsheet. Okay, everyone ready? No? Okay. Thank you. Very helpful. Okay. So now we have this technology matrix already compiled, and then reference flow here. This doesn't mean anything. I will just remove this. And then the B matrix, environmental matrix, elementary flows are over here. What we now want to do is to calculate the A inverse. So A inverse, what it means, I will show you what it means later, but what it means is that, well, basically what is the direct and indirect requirements of each chemicals to produce 1 unit of each. And it will be very interesting to see that. Yes, please.
Sure. Could you just briefly cover the flow terminology, intermediate flow, elementary flow, reference flow, just so we have it all in one piece? Thanks.
Sure, absolutely. Yeah. So the question is, what are the definitions of the elementary flows and intermediate flows? So intermediate flows are, you can think of intermediate flows as products or services or chemicals that are man-made. Someone made it through anthropogenic processes. That's intermediate flows. Elementary flows are the flows directly coming from the nature or outgoing toward nature. So ISO definition of elementary flow is the flows drawn from the nature without prior human transformation, or flows going out to the nature without subsequent human transformation. Generally, what that means is natural resources we are extracting or environmental emissions that we are generating. So when we say environmental impact or natural resources impact, it involves elementary flow, right? That's why life cycle inventory is measuring the elementary flow. We are not measuring intermediate flow. We are interested in measuring the elementary flow, but in order to do that, we need to understand how much of intermediate flows have been generated to produce the chemical or the activity of my interest. Yes? No? Okay. Okay, great. No worries, thanks. Now, let's first, even if you worry that, well, I'm not sure what I'm doing, that's okay, but let's do this, and then, well, we'll try to explain what it is. So let's first select this whole matrix here in the yellow marked. Select this whole matrix. So click the first cell and then just move around toward the end. Yeah? okay? And then you press the keyboard equal sign, and the magic word here is M inverse, which stands for matrix inverse. And then open the parenthesis, and then you go up to the A matrix and select the entire A matrix. If I'm too fast, let me know. I'm too fast. Okay, I'm
No matter where you start on the selection of the A matrix.
You want to start from the beginning to the end. So, you know, first column, first row to the last column, last row. And then close the parenthesis. If you have done this, it will show up the equation like this, the function like this. And then everybody really pay attention to me. This is very, very important. This is really the where the most of the trouble comes. You might have never done this before, but try to press Control, Shift, Enter all at the same time. Control, Shift, Enter all at the same time.
Okay.
Have you done that? How many of you say that this is the first time that I ever hit those three keys together? Great.
It allows you to paste and work with the as opposed to a single step.
Exactly. It calculates. Exactly. Yeah. It's array calculation. So what it does, what you just have done, is to calculate the inverse matrix. How many of you succeeded producing this result? Excellent. If you have not, please raise your hand, and Munya will walk around and help you to do that. Okay? Great. So Munya, after Carr, we have another participant here who will need your help. Great. So now let me kind of explain what this really means. Okay? So what this result that you are seeing really means is that, well, if this A matrix was constructed correctly, each column is very useful for us because each column tells us what is the life cycle requirements of each element, each rows, to produce 1 unit of itself. So producing 1 unit of methylene chloride, we now know throughout this upstream life cycle processes, we need 0.6 kilograms of chloroethane and 0.82353 kilograms of chlorine, and we also need hydrochloric acid, although it did not require this directly, because it requires hydrochloric acid throughout the upstream relations, right? So each column is very meaningful. Each column is very meaningful, not only for methylene chloride, but also you can calculate the same life cycle inventory for chloroethane using this column, or chlorine, etc. So this is a very useful matrix. Now, we want to understand what is the total amount of inputs needed throughout the life cycle to produce 1 unit of methylene chloride, which is basically this column, right? Yeah. So the activity levels are simply, you just copy this column and paste it over here. Yeah. For those who enjoys using matrix calculation using Excel, another way to do exactly the same thing that I just did is to select the entire area like this, and then put an equal sign and put mmult, which is matrix multiplication. And then, well, first you select this A inverse matrix, and then comma, and go up and multiply this with the reference flow matrix. And then close the parenthesis, and again, Control Shift Enter. If you do that, it will basically do exactly the same thing. So basically, what it does is that, well, you extract the first column based on the reference flow. And you remember that in our PowerPoint file, we did just that, right? A inverse times Y. will be the activity level, or the amount of inputs needed throughout the life cycle. That's what exactly we did right now. So either way, you will get this activity level. How many of you have reached this level? Okay. Okay. That's fine. You're working on it, so we'll give you a little bit more time. And if you need any help, just raise your hand so that I can walk to you, or Munya can walk to you. So let me just very briefly recap what we have just done so far. So what we have done so far is, first, we just made an inverse matrix of the intermediate flows, A matrix, technology matrix, yeah, just intermediate flows without involving any environmental emissions. That is this. And then the second thing that we did was that we multiplied the inverse of the technology matrix to the reference flow vector. Or you could have just copied and pasted the first column to this cells, just the numbers. That's what so far what we have done. Yeah, are we good? Mm-hmm. Yes, please.
Reference flow, then it wouldn't update your activity levels, right?
Exactly. Yeah.
Okay.
If you do the matrix multiplication, then if you change the reference flow vector, it automatically calculates the activity level. Right. So that's why I personally prefer matrix operations rather than copying and pasting, especially when you are actually working on this. If you keep copying and pasting, then later on you don't know, where the number come from. But if it is written in equations, then you can trace back where those numbers are coming from. Great question. Now, our next step is to calculate your first and ever lifecycle inventory. So, lifecycle inventory, again, is the total amount of elementary flows coming in and out of your system throughout their life cycle. And what we do is very simple, because we know how much of the chemicals throughout their life cycle need to be produced throughout the upstream of methylene chloride. And we know what is the environmental emissions or elementary flows needed for producing one kilogram of each, right? So if we multiply the amount of elementary flows needed for producing 1 unit of each to the amount of chemicals need to be produced in order to produce 1 kilogram methylene chloride throughout the life cycle, then we will be able to calculate total amount of elementary flows needed for producing 1 kilogram of methylene chloride throughout its life cycle, right? What does that mean is that we can just do very easily. First, select this entire cells. These are the elementary flows that we have in our data. And again, the same thing, equal sign, and M mult is our magic spell. And we first select B matrix. So 2 matrices are being multiplied, and first matrix is the B matrix, and then you put comma, and then the second matrix that you are multiplying to is the activity level. Because, and then you close the parenthesis, because what we are now doing is that, well, we know how much of chemicals are needed, and we know what is the environmental emissions of each chemicals per kilogram, and we multiply those two. And again, Shift Control Enter will generate lifecycle inventory. How many of you have got this so far? Great. How many of you need help? Okay. Munya, if you can help. Yes. Once again? Absolutely, yeah. After the inverse, right? After the inverse matrix. Yeah. Okay, great. So I will do it once again. So basically what we want to do is to multiply the B matrix to the activity levels to arrive at total life cycle emissions. Because B matrix is just a direct emission from each process. And in order to calculate the life cycle emissions, we want to multiply that to the total amount of chemicals produced. What we do is that we select the entire vector of LCI, and then put equal sign and put M mult, which stands for matrix multiplication. Open the parenthesis, enter the B matrix, select the area for B matrix, and put comma in between and select the activity level, which is X vector, and then close parenthesis and hit the Control Shift Enter all at the same time. And then you have the life cycle inventory. Okay. Yes, please.
Sorry for another question.
No worries.
We just have a little confusion around multiplying the results of A, which is one set of chemicals, times B, which is a totally different set of chemicals.
I see.
It's a little confusing.
Got you. So the A matrix is all intermediate flows, meaning that they are the chemical products or other products. B is emissions. These are elementary flows. These are not products. These are not manufactured products. These are the emissions to the environment. Yes.
Is it possible to conceptually show that on the flow chart where you have the arrows producing the different elements to produce methylene chloride?
Exactly. Yeah.
Capture?
Yeah. Absolutely. Yeah. We can do that. So I can just show you. So conceptually, what this all do, I think that's a good point to actually show this more visually. So what this is doing is this. Here you see that these are, so we just have done this part. So what we have done is that, well, these methylene chloride, methyl chloride, chlorine, other, methane, chlorine, all these are intermediate flows, right? Yeah. And what we first wanted to do was to calculate the amount of intermediate flows needed in order to produce 1 unit of methylene chloride, right? That's what the matrix inversion, A matrix inversion times the reference flow vector did.
Right.
So that one calculated the amount of intermediate flows needed. But then, well, each of these processes have the elementary flow inputs and elementary flow outputs, right? And we wanted to understand exactly that. So what we did was to multiply the direct elementary flow exchanges of each processes to the total amount of product needed throughout the life cycle for producing 1 kilogram of methylene chloride. That's B matrix times the activity level, which is X vector, the last operation that we just did. Yes?
The waste and emission outflow in your schematic, is that captured in B?
Basically, it should be in B. So because our example is very simplified, we didn't have waste. However, in the complete B matrix generally goes like about 2,000, 3,000 rows. Yeah. So it captures all the natural resources and waste exchanges too. Yes, please.
Can you just briefly explain the difference between the water consumption in the intermediate flow matrix and then water in the elementary flow matrix?
Really good question. So water consumption in intermediate flows means that water treatment facility, treated that water and shoot it to you. They are selling that water to you. In that case, is that elementary flow or intermediate flow? Intermediate flow, exactly. The water in B matrix is the water that you are pumping from, a reservoir, or it can be groundwater. In that case, is that elementary flow or intermediate flow? Elementary flow, exactly. So that's that. That's the difference, basically. The same water can be intermediate flow or it can be elementary flow, depending on whether it went through the human transformation prior to receiving that the flow. Okay? Yes, please, in the back.
Why the numbers in matrix A are negative numbers? Does that mean when you produce sodium chloride and you save water, the water consumption, for example, that column is say negative 0.001?
That's right. So negative values in the A matrix refers to consumption of that flow by that process. So positive values refer to production, negative values refer to consumption. So if we go back, negative flows are all the consumptions. Positive values are the productions. Yeah?
The production of electricity, plus production of the natural gas, there's the ones, all the ones.
Production of electricity is here. So this is electricity process. Producing 1 megajoule of electricity seems to require 0.01 kilogram of water. I mean, these are kind of fake numbers, but that's kind of the logic, you know. Yeah. Okay. It should have required some natural gas or coal, things like that, but this is truncated for the sake of simplicity. We didn't want to make you invert 11,000 by 11,000 matrix here. Okay. Now you got your life cycle inventory for methylene chloride, but that's not the end. Scroll your screen to the right. There's another beast waiting for you. Okay, so here there's benzyl alcohol, and I will not give you instruction here. I will let you calculate life cycle inventory of benzyl alcohol using the example for ethylene chloride. So there were a few questions that I would like to kind of revisit to the rest of the group. So one question was, what if there are more environmental emissions than 9? So it was actually coincidence that these are also 9, and these were also 9. Actually, they do not have to match. Yeah, so you can have 200 or 2,000 elementary flows generated by 9 processes, and then in that case you will have 2,000 by 1 vector for life cycle inventory, and you can do the same calculation. Another thing is that one trick that which I didn't tell you was that actually you can calculate the life cycle inventory of benzyl alcohol by just changing this value. Instead of reference flow, putting reference flow of methylene chloride here, if you put 0 here, so actually, no, I'm sorry. So we have different A matrix. So if we have the same A matrix, actually we can calculate benzyl alcohol. If benzyl alcohol was included here, then we can just turn off methylene chloride and turn on benzyl alcohol to calculate the rest. Yeah. But in this case, we constructed different A matrix, so we cannot do that. Yeah. So in that case, let's move on to the next topic, which is life cycle impact assessment. Yeah? So any questions before we move on to the impact assessment so far? Yes.
It might be repetitive, but conceptually, if we look at the flow chart one more time, if we could show what the matrices we generated,
how does that relate between this calculation and the flow chart? Yeah, I think that's a good call. So let me go back to the slide and show how those two are related. So basically, what we are seeing here is the production of methylene chloride. We have the tree structure. These are the inputs needed for methylene chloride directly or indirectly. That's very important. Not only directly, but also indirectly throughout their upstream life cycle. These are intermediate flows, and the relationship among those processes are recorded in the A matrix, technology matrix, inversion of which will tell us direct and indirect requirements of those chemicals, those inputs, right? And then, well, we still do not have any information on elementary flows, which is stored in the B matrix, which is the elementary flows for producing 1 unit of each output. So what we did was that, well, first, we calculated total amount of intermediate materials or product needed to produce 1 unit of methylene chloride and multiplied the elementary flow matrix to that amount to generate total life cycle inventory. So in a matrix, basically this interrelationship among processes are stored in A matrix, and A inverse times the reference flow vector will generate X, which is the amount of total amount of materials needed to produce 1 unit of methylene chloride throughout its life cycle. And if we multiply B to X, B times X, B is the elementary flow matrix, that will give us the life cycle inventory. Does it help? Okay. Great. So it does take some time to sync this information, because it's so long time ago since you have done this, but these are not rocket science. as you can imagine. This is actually much easier than actually what you are doing to day-to-day operation. So if you take some time and revisit after this workshop, just take a look at what I have done once or twice more. I think that it will go very easy. Okay. Now let's look into the life cycle impact assessment side. So we have gone through this, and the second topic is life cycle impact assessment. Now we have the vector M, which is life cycle inventory. Again, that was calculated by B times X. That's what we have done, right? Now, we want to characterize that. So characterization that we talked about yesterday is basically aggregating elementary flows into environmental impact scores. That's what characterization is for. The most well-known characterization factor, as we talked about yesterday, is global warming potential. So basically, we are aggregating CH4, N2O, and CO2 into all CO2 equivalency, right? That's what characterization does. And for toxic chemicals, we use the similar process. We identify what is the reference indicator, and then we aggregate the toxic impact based on that reference indicator, just like we do with CO2. And that is stored in CF, which is characterization factor matrix. This characterization factor matrix basically shows what is the relative magnitude of environmental impacts of different chemicals. So in this example, what we have is that, well, NaCl, NaOH, and HCl, these are the elementary flows, and these rows shows the respective environmental impact relative to each other. So in this particular case, it seems that we didn't put any human health impact for the urban air emissions for cancer. So this carcinogenic impact is all zero except for the CH2Cl2. So that one has, we have 0.00001, and all the rest is a zero. That's easy then. Well, ecotoxicity characterization factor for fresh water, we have a few elements that goes into the category. As you can see, the last three, the third and second to the last column. Global warming to air, we do have a few substances such as CO2 and CH4 and N2O. Actually, it should be N2O, not NO2, N2O, having some numbers there. And water consumption, let's ignore the water consumption row for now. Actually, it was a mistake. So we should not think about the water consumption. So let's focus on the first three rows for now. So it should give us the idea on the relative magnitude of impact by each substances contributing to these environmental impacts. That's what characterization factors is about. So what we do is that, well, basically we multiply the characterization factors to life cycle inventory. That will calculate the characterized result. Actually, there's one more correction that I forgot to do, which is that, well, we have to do this instead of I minus A. There are two different traditions, so sometimes our students are confused, but this is the correct form, actually. Okay, so in the Excel spreadsheet, what we have is the so normalization is the next step. So we, in the Excel spreadsheet, we do have the characterization factor matrix. So basically, we can just multiply that to life cycle inventory. That's easy. And then the next step is normalization. We talked about normalization yesterday because each characterized impact is having different units. So it does not really mean very much for us to understand what is the relative magnitude of that impact of this chemical that we are interested in. So we want to divide that by the national total or global total or regional total, depending on the scale of the environmental impact that we are considering. So we have the national total impact of these impact categories in our spreadsheet. And then we also have weighting factor. Yesterday we talked about, okay, even if we have done the normalization, we don't know what is the relative significance of different environmental impact categories. Yeah. So we talked about, well, it requires some subjective decisions, and that subjective decision can be materialized in numbers as weighting factors. So in this particular example, human health impact is weighted as 2.9, and global warming air is weighted 1.1, which is arbitrary, of course, as compared to. So yesterday I have shown you the EPA panel weighting factors that gave us much higher global warming impact, global warming weights as compared to human health impact. But this is just arbitrary number for the sake of our exercise. So let's go to the Excel spreadsheet once again, and then you will see the LCIA tab here. Now, what you want to do is that, well, you don't have to recalculate all the inverse and life cycle inventory. You can just copy and paste what you already have calculated here. Life cycle inventory. I will just copy and paste just the numbers in this case, because you don't want to paste whole equation because we don't have that numbers here. Okay, so now I have life cycle inventory, and LCIA result is again simple matrix multiplication between characterization factors, which is here, CF, to life cycle inventory. So I selected these 4 cells. Actually, it should be 3 cells, but let's for now let's do the 4 cells, and then we'll have M mult, and first select characterization factors, and then comma, and then life cycle inventory here, and then the same trick, Control Shift Enter will generate characterize the result for human health, ecotoxicity, global warming, and water consumption. So for the first time, we are now generating environmental impact scores. Before it was just a list of elementary flows and their quantities. Now, we are now talking about environmental impacts. Before it was just flows. Now, we have aggregated those flows into environmental impact scores. So this is a characterized result that you are seeing here. Let me just go, so how many of you have completed this step so far? Great, great, great. How about you?
I deleted everything that I had before.
Okay. Well, that does happen.
Right.
Yeah.
Realizing we're going on to other pages.
I see. No worries. You can probably, Munya, if you can help our attendee to recreate that quickly, yeah, that will be helpful. Okay. So once you have done that, then you can go on to the next step. So once you have done that, it should have automatically generated a figure. Yeah, okay, great. And then you can go on to normalization too. So normalization basically is easy. So basically you are dividing each of the characterized result by the normalization reference. So I will select that, well, you divide the first characterized result by the first normalization reference, and then you just drag that down to calculate the normalized result. And it will show the normalized result chart down there. And then the next step, I will just explain this so that you can just go through. Some of you will come quick, and some of you will take more time. So I will just go through it and walk through the tables. The weighting is basically matrix multiplication. We select these weighting factors to the normalized result. And then Control Shift Enter will generate weighted result. Yeah. Now, conceptually, what you are doing here is to aggregate a whole bunch of elementary flows into impact scores through characterization, and then those impact scores into one number, weighted impact. That's what normalization and weighting does. So basically, we are distilling the elementary flow information into impact scores. So we are aggregating them into into impact numbers. Obviously, while we are doing that, we are losing information because these weighting factors are uncertain, normalization references are uncertain, all those things. But for decision making, sometimes we have to make those decisions based on the trade-off situation. Then weighting, normalization weighting could be one of the approaches. Now, I would like to ask you to work on this and the benzyl alcohol for the remainder of the session. We have about 10 minutes, and while you're doing that, I will just walk you through so that if you have any questions, you can raise your hand so that I can help you. So once you have done the calculation for methylene chloride, please proceed with benzyl alcohol and compare those results and see whether it makes intuitive sense to you. And as you can imagine, it really depends on how you do the weighting, how those characterization factors are set up, all those kind of things come into play. So think about that, and please, have those comparisons with you. So by the end of, so in about like 8 minutes or so, I will ask you which one would you prefer as an alternative, as a result of the weighted results. Another quick remark is that in this exercise, we haven't done the contribution analysis, but I have written a book about how to use this kind of techniques to do all kind of interesting analysis, including contribution analysis. So yes, it is possible to do contribution analysis. We can decipher this result and see which process contribute how much, which elementary flow contribute how much, all those kind of things are possible. We don't have enough time to go over that today. Let's wrap this session up. There are a few things that I would like to mention before we close. Okay, so first, why do we do all this math using matrices? Why this is a better idea than just manually calculating all the elementary flows and life cycle impact. You can also do that. You can just draw the process flow diagram, the tree structure, and manually calculate that. But then we'll think about what to do with the sensitivity analysis or uncertainty analysis, Monte Carlo simulation. If you are running Monte Carlo simulation for 10,000 times, you have to do 10,000 times of the manual calculation. That's not very convenient. So this structure, this framework helps you to extend this analysis to sensitivity analysis, contribution analysis, Monte Carlo simulation, uncertainty analysis. All those kind of things become really easy. So we do that all the time. We do Monte Carlo simulation, sensitivity analysis, compare two different results using standard deviation figures, all those kind of things. Really, this one facilitate and accommodate all this more fancier analysis out of that. That's one thing that I want to mention. Second, one of the good students in this room reminded me that, well, yesterday we talked about functional equivalency between benzyl alcohol and methylene chloride. Can anyone remember? Do anyone remember that? Yeah. Yeah? Okay. 1 gallon of methylene chloride was 0.83. Yes, great. 0.83 gallon of benzyl alcohol. So in this particular case, we compared 1 kilogram to 1 kilogram, and that will be wrong, right? Because those two, 1 kilograms will not really compare in terms of functional equivalency. So what you can do is to change the reference flow vector of benzyl alcohol to 0.83, and it will recalculate all the rest of the impact, and then you will repopulate the graph over here. Then you can compare those two chemicals on the same functional basis. Now, what was your result that you got in terms of the weighted result for benzyl alcohol?
Isn't that wrong now? So you missed the reference?
That's right. So we have to go back and let's change that to 0.83. Yeah, let's do that 0.83 right now. And probably you need to copy and paste again. Yeah, 0.83. Here is the result. So this is weighted results, and probably you got the same numbers. Let me ask you a question. Can you say whether benzyl alcohol is better for the environment throughout the life cycle as compared to methylene chloride based on this result?
It should be empty, right?
Hmm? No? Why?
The weighting is an assumption
We made, yeah, this is subjective assumption, but that's, you know, someone has to make
Right.
that assumption.
But for global warming impacts, benzyl alcohol is higher, so if that's your priority.
If that's your subjective judgment, then, well, this result still hold. But how about uncertainty?
Yeah, the difference is too small relative to the uncertainties in the.
Here we go. So the difference here is how much? It's about like 40%, yeah? But it's the same order of magnitude. And as we talked about before, characterization factors, normalization references, and incompleteness of life cycle inventory, all those things does not really make this much of difference really significant. Of course, it does have some meaning. Okay, it is likely that methylene chloride will have higher life cycle impact overall based on our judgment on the weighting factors, all that. However, still, given all those uncertainties, how significant this difference is still question.
Okay.
And that's what we will do in this afternoon. We will look into the data sources and how certain are we on the data source on those data sources, and really think about, you know, how to interpret this result, considering the underlying uncertainties associated with the data sources. So even if you got this deterministic result showing 20, 30, 40% of difference, we should not necessarily go quick and come up with a conclusion, yes, benzyl alcohol is much better throughout this life cycle. We may not be able to make that the really firm conclusion based off of this type of result if we consider the uncertainties involved in these numbers. That's the last thing that I just wanted to communicate. Yes?
The scale that we use for normalizing the different parameters, it has to be the same scale?
It has to be the same scale. Yeah.
National or local?
Yes, in principle it should be. Yeah.
Okay.
We are assuming that they are in the same scale in this particular example. Yep. Great. Yes.
But what do you do when they have different impacts, right? That's not the same. Like when you were comparing the alternatives yesterday, so like sandblasting versus water-based, I mean, they're kind of like really different flows and impacts.
Yeah.
So how do you?
So that's basically the question of how do we assess trade-offs, right? So if we have, even in this particular case, based on the normalized result, benzyl alcohol is showing higher impact as compared to methylene chloride on global warming. So if you happen to have high priority, if you happen to give high priority on global warming in your weighting factor, you will see a completely different result. And we can actually test that very easily by changing these numbers. For example, if it is not 1.1, but what if it is 10? And what if this is not 1.1, it should be the same. So, sorry, not this one, but the other one. If it is 10, then let's see, what is the weighted result looking like? So see? So it is very sensitive to the relative weight that you are giving to different impact categories. So how to navigate this trade-off situation in the presence of subjective judgment is a real challenge. And there is no firm science that can help you totally eliminate subjective judgment. Subjective judgment is part of the process in life cycle assessment. I think it applies also to AA. The question is, how can we justify this in interpreting these results? And that's the thing that is show your work part. So it should not be totally arbitrary as long as those subjective judgments are made under good reasoning. I think it should be justifiable. But it suffice to say that these results are very, very sensitive to those subjective judgments, as you have seen here. Yep.
So I'm a bit confused still, because yesterday we talked about some specific localized parameters. And then when we're doing the normalization here, we're doing something applying the same scale, regardless of anything localized. So how do we account for it? Is it a weighting factor or a different parameter that comes subsequently and after normalization?
Right. So In principle, normalization reference and weighting factors should be based on the same scale.
Okay.
So as long as they are derived in the same scale, this is classic problem of congruency between normalization and weighting. It has been well documented in the literature in life cycle assessment. So as long as they are in the same scale, conceptually they are at least consistent. So in our example, we just use all national scale for the sake of simplicity, but in reality, those congruencies should be given between those two. Yep. Okay. Great. I'm eating of your coffee break, so I wonder, can I propose like extending coffee break 10 more minutes so that we come back at 10:50? Carrie? Okay, thank you.
Okay, so again, welcome, and we're going to do these hands-on exercises for the exposure assessment, trying to give you an idea of how we go about doing some of this, where do we get the information that is needed, using first some simple models to do some of the calculations, and then showing you where other tools that are available so you can actually work with more sophisticated tools as needed. So we're going to be talking about these hands-on examples. So if we go to the third one, two different exercises. First, we're going to be working on how do we calculate release, or how much is used of the product. So trying to get an idea, and we're going to take a look at both the bottom-up approach. We go and find the information on how much of this product is likely to be used, and what are some of the information that we need for that calculation, as well as we're going to take a look at a top-down approach, where we start from the top, trying to figure out, okay, how much is used and nationally, and then bring it down to kind of scale it to a regional level. And so we'll do both of those exercises. And to make it a bit more interesting, we're not only going to stay with the paint strippers that we've been showing you now for quite a few examples, but also work with shampoo and look at some of the ingredients in shampoo. There are concerns with some of those. There's, talks about replacement of some of these. And so we'll take a look at some of the information. So that will be the first part. And then we'll move on to moving on to the exposure amount and how do you estimate that? So we'll use an indoor air and a dermal model. So we use two models for looking at both the paint strippers for the indoor air and dermal for the shampoo. And then we'll go to a tool that's available freely online, Consexpo, which can help us to do these, again, for these calculations. It provides a lot of the exposure factors. So even though we'll show you how to get them, you can use the ones they provide for you. And then we'll take a look at, in our tool, we can also do indoor, outdoor exposure, dermal exposure. So we'll take a look at that using the click tools. Okay, so first, what are the chemicals? So the first thing we need to identify is what are the chemicals. We've already seen these two, methylene chloride and benzyl alcohol. The ones for shampoo are methylparaben. How many people are familiar with parabens? Okay, so good number, good. It's interesting now you walk into Whole Foods, and as you walk in, the little towels that they give you out for you to clean up your hands say no parabens. And I wonder how much people know, but apparently enough that they are now putting it out there, no parabens. So it used to be we thought, parabens were very non-toxic, and there's now concerns about some of their toxicity. So that's a class of antimicrobials that is becoming an issue. So there's these two other options, and the manufacturer could figure out what are the trade-offs. I think many of them are moving away from some of the parabens just because of some of the concerns, the public concerns, and so there are trade-offs that have been evaluated by different agencies. So these are the three chemicals that we'll be looking for in the shampoos. Okay. So first is how do we estimate release? And so we're going to go through and first look for our data. So one source of data, we gave you a number of them. We're going to go to this PubChem and take a look at data for one of these compounds and show you the type of information that's available for you as you go through these different exercises. So this has benzyl alcohol. It provides us with data, a lot of information. So this is a really good source of information. Not the only one, but there's a very good source. There's many places now where people are integrating it, and it has information on the chemical. And as we scroll down, it will have information also on things like the chemical and physical properties that we talked about yesterday, the toxicity, So it has a lot of this information. Now, it can be overwhelming, particularly the toxicity part. Let's let's go first to the chemical and physical properties. So here we'll find that it will have, as we scroll down a little bit, it will have our vapor pressure, so it's coming up a little bit more. So our boiling point, melting point, flash point, solubility, so water solubility, how much it's soluble, density, and so on. So we can find a lot of this information here. And again, yesterday there was some comments that some of these values are different in different databases. So that's a challenge that we have. Depends on where it is. Good thing here is they provide, in general, what is the source of that information, so we can actually see what is the solubility for many of these compounds and the various physical chemical properties. Now let's go to the toxicity information. So here, the toxicity information is provided. It gives kind of a summary. This is something that, this chemical does have some skin and eye irritation, so it provides some of that and, some of the doses. Talks a little bit about some of the health effects, inhalation symptoms. And then as you start getting into it, you'll find that it has a lot more information, interactions, and then more detailed toxicity. So what I mean is it can get pretty overwhelming in the sense that there's a lot of information, but it's a very good source and captures most of the most recent studies on the chemicals that you may be interested in. So it's a good source. PubChem is a good source for finding a lot of this information. Any questions on that? Okay, we'll take a look later on at some of the other ones. We're also going to go to this ChemID. ChemID is another good source for information. It's provided by NIH. And again, a lot of the information is here. It can be used for looking for this information. And you will see, it has the toxicity information and the properties just as well. So we can go to toxicity, and this is for the methylparaben. And so we can see, for example, some of the information that would be needed for us to do some of the calculations for, the risk analysis, the risk assessment. How do we know that, a particular exposure dose is going to be an issue? So they provide that kind of information for us. Okay. So again, we're going to gather all that information. So let's go now to the next point. So we've gathered that information for you, the information that's most important for us. So the structure, the molecular weight. And so here's what we have. These are mostly solvents. They're used in paint strippers and many other applications. These are mostly used in personal care products to preserve the product. And here are some of the values. So we have the vapor pressure, the solubility, the octanol water partition coefficient, the half-lives, and again, these are estimated from various sources. Many of these are estimated from EpiSuite. So we use a predictive tool to get some of these values if they're not available in some of those websites. And so, once that's a EPA-based estimating tool for many of these properties. And so we can see, for example, that methylene chloride, as we saw yesterday, is extremely volatile, very volatile compound, whereas benzyl alcohol is a lot less. These are even less, so these are unlikely to be significant in indoor airs, even though you're using them in a confined space like the shower. So it's not going to be a significant exposure, but you could put that into our indoor air model just to see whether the indoor exposure, inhalation exposure would be significant. Solubility, these are all fairly soluble. This one's a little bit less, so these compounds in general would be relatively soluble. Not significant bioaccumulation, except a little bit by methylparaben. So we wouldn't expect a significant amount or any relevant amount of bioaccumulation. And in terms of the half-lives, methylene chloride is the most stable one. And so it has chlorine, tends to stabilize compounds, so it's the most stable one. And again, when we look at the half-life of benzyl alcohol, this is, particularly the one in the air, is in the outdoor environment. And so when we use our tools, we should be careful to think about where is the use and is this information as relevant. So we'll take a look at that. Yeah.
But just a quick question, the half-life in air, how relevant is that going to be for chemicals that have really low vapor pressures?
Not very relevant. So yeah, right. So for example, for these, it's not going to be very significant. We will see some in our atmospheres, but the concentrations are going to be very low, and these half-lives are short. So if they do get into the air, they would disappear fairly quickly. But in terms of the overall exposure, I think which was where the question was going, probably not very relevant. Yeah, which goes back to the relevance point that we made yesterday. Thinking about what are the relevant factors that you need to consider. So good point. Yeah, thank you. Okay, so that gives you our values for this. And then we take a look at the toxicity available. This is another very good source. Before I showed you PubChem, EPA has not put together this dashboard, which has a lot of the information that is also needed. So we wanted to show you different sources of information. This has information on the non-cancer RFD that we talked about yesterday, the LOAELs, the lowest observable adverse effect levels for these chemicals, and then the cancer information. But because these four are not classified, there is no data. There may be studies, and so if you go to PubChem, you'll see some studies that are issues. One of the issues with methylparaben, some people have shown some issues with tumors. Others are endocrine receptor disruption issues. So that's why it's being now considered something that manufacturers may want to get away from. So that's the concern. But so far, it has not been classified. So we would not have that information for the assessment here. Okay, any questions on that? Okay. So we're going to go and take a look at where do we get some of this data. So the first one is going to the EPA Exposure Factors Handbook, and we'll take a look at some of the information. I've shown it yesterday, but today we're going to sort of zoom in a little bit more and spend a little bit of time with the information. So this is the Exposure Factors Handbook. This is the 2011 edition. A lot of the data has been compiled over several decades. So even though it's the 2011 edition is the most up-to-date, some of the information, as we saw yesterday, is not necessarily a very recent study, but many of these factors are very valid. If you know that there's more advanced information, of course, you should use that, but this is a very good starting point for all your calculations. So we're going to go to the page for the paint removers, paint strippers. And for example, here it's collected before we had it in several tables. This one collects the information. What is the amount per use? So what's the likely use of this product? So 65 for 64.84 fluid ounces. And again, going back to some of the questions, it actually provides you with, kind of the whole distribution. So later on, when we see some of the tools, you could use either a distribution for this, or you could use the 90 percentile, the 95 percentile, 95th percentile. And then again, how much is it being used? How many minutes people use it? How much do they stay in the room? So it gives you an idea of what's the likely exposure. So very useful information for doing a preliminary estimate. And if this is all that gets you to the answers, that's great. If you find that you have more recent information or more applicable information for your product, that would be also useful. The other one we'll take a look at is for the shampoos. So again, take a look at that. This is the amount and frequency of use. And so, for example, here we have different products and some of the shampoos, looking at the amount per application. And then this information actually is coming from a manufacturer. So it's actually, they've done their studies and provided that to EPA. So some of this information is very industry relevant. Others were done by other organizations, so it helps you to give you an idea of where you may have that. And the average frequency of use and the information in terms of the upper 9th percentile. So it gives you that, which is what would be typically considered. Okay. Any questions? Okay. So let's move on to, so now we have our data. So bottom up, we would actually take the information that we had and do the calculation, and then that gives you the idea about the exposure per person, so the chemical. For the top down, what we do is go ahead and take, what's the actual production of the chemical, if that is known, or what's the estimated production, and how do we then bring it down? We use market studies to take a look at, what are the typical categories in which this product is used. So for these two chemicals, benzyl alcohol and methylene chloride, this is the amount that's used in paint strippers, about 25%, and out of that, about 50% is used by consumers. So that gives you some per capita consumer uses for these different compounds. So it's coming from the top, trying to figure it out, and they end up matching fairly well. And it doesn't always happen, so I think it's always useful to do the bottom up and the top down, just to get a reality check if you're using this, if possible, just where are you with respect to the amount used in terms of kilograms per year per person to get a sense of the exposures. Yeah.
When you do it top down,
Yeah.
and you look at collection of chemicals,
Yeah.
Do you know for sure that all those chemicals are used within the country? Or?
No, you don't. And so there could be exports, imports, and so it's a little bit challenging. A lot of times this information is proprietary business information. So if you are a manufacturer, you may have a good sense of where that is. But if you're kind of an intermediate producer, you're the one that makes the paint stripper, or you're the one that makes the shampoo, you may not know that. So it's always challenging to do that. So that's why we use both approaches to try to get an idea. And sometimes we can do it from the top down. Sometimes we don't have this information, so we then use the bottom up. So I'm just giving you the two ways to try to get at the information, because that's really challenging to do that. Okay. So let's take a look at our tool, and we'll see how we do these types of calculations. So we're going to use the release tool, and this is something that Mungia spent quite a bit of time developing this tool, so I want to give her credit for that. So this is maybe should we go just from the beginning just to show them how we actually, so once you get into the tool, again, as Sangwon was mentioning, we will be releasing this in the near future. Once you've logged in and are into the tool, you have the way to look at 3 different modules or sets of modules. One of them gives you kind of screening level analysis, provides a lot of the properties, some of the hazards, and environmental impacts that may be provided. So gives you kind of a dashboard or a score sheet that you can use to sort of get an idea at what are some of the major issues with a particular chemical. The other one is the one that Sangwon will be talking about later on, is the Lifecycle assessment modules. So that gives you a lot of the calculations that he was showing. And then we're going to be using the risk assessment modules now. So this allows you to do a lot of these calculations, how you go from, okay, identifying your chemical all the way to release, exposure, concentrations, and risk assessment. So we're going to go to this one here, just any project in. Right. You do need to have a name, so that's the only thing. To get it going, you then have to have a name. Right.
Do you want to do shampoo or paint?
Shampoo, let's do shampoo. Mm-hmm. So first thing you do is you can estimate just the chemical release if that's all you want. And so we'll do that at some point. You can do chemical-specific environmental concentrations. Maybe you already know some information, you know your release, so you don't have to do that, so you do this directly. You can do human health risk, ecological risk, or human health and ecological risk. So you can do different types of modules depending on what your objectives are. So if we select this one, then it will do all of these. It calculates that, and yeah, we can put those for now. So you can do chemical release, these environmental concentrations, dermal risk. We won't do indoor because it's not very significant for these. And then we're not going to use this now, but we could enter the information as a formulation. So one thing we thought would be very useful for people who are working with consumer products is that many times they're formulated. And so you'd like to get an idea of what's the impact within the formulation. So you can input your chemicals as a formulation, and then it will do the calculations for all of them. And so that would require that you have very good knowledge about that. So if you do have that, you can treat them as a formulation. So we can go ahead and create the project. Yeah.
We're looking at personal care products, right?
Yes.
Don't some of them have like pretty strong smells though? I mean, on their
the shampoos
and other things in there. So I'm just curious why you're ignoring the indoor.
Just for now, we don't have to ignore it. Just for now. But for example, many of them have fragrances, and so that's where you get the smell. It's not from these preservatives. It's from the fragrances. No. So if you wanted to evaluate that, you could then put a formulation and keep the indoor air exposure. We could also have kept it in there, and we would find later on that it's not very significant. So I'm just sort of saving a little bit of time. But yeah, very good point.
Just to add that,
yeah.
Because the smell, that's another thing that you are exposed to high level.
Yeah.
Oh yeah.
It's kind of different water threshold.
Yeah. Right. Right.
That's why I was asking the question.
Yes. Right.
But I know that some
Yeah.
fragrances have carcinogens and other.
Right.
Important to evaluate.
It's important to evaluate them. So you could certainly add them. Just you don't have to exclude it. That's correct. Yeah. And the good point is, the other point that you made is very important. Sometimes we can smell things at parts per billion levels. There are some chemicals that are we're so sensitive to them. So even 1 part per billion, you notice it. And yeah. Right. Okay, so then that provides us with the project, and it's a shampoo. We're going to be calculating these things. And because we want to make the calculations region specific, then the other thing we need to select before you even get to the chemical is what regions do we want to use. Right now we'll just use one, but we have to select a region. So let's take San Francisco. So we've added in the tool, we've added in about 24 different regions that we have around the country, and some of them are also European regions, so that we can actually get an idea of what are the situation in Rome or Sweden, New York, and so on. And we're constantly adding to that as we have more partnerships that we can work on. Some of them are very large cities, some of them are small, as you saw, Des Moines, Iowa, or Visalia in the Central Valley, just to get an idea of what would happen under different circumstances. Okay, so now it also allows us to pick. It gives us the population for that region, and then also has a lot of information about the region. We're not going to go through that, but it has the information that we need for us to do the calculation. What's the land use? What's the climate? What are the soil like? All the information that's needed for that. So go ahead and save the region. And then now we're going to pick our chemical. So we're going to add the chemical, and we'll use methylparaben. So as someone was mentioning yesterday, some chemicals have multiple names. So if you enter a name, it will go through, and that's why it takes some time, checks our database, and if it finds an immediate match, then it brings that right away. If it finds several matches, it will allow you to pick which one you think is the correct one. And, then that will be right. You have to we'll provide you with the structure for all the ones that you have, their formula, their chemical abstract services registration number, and also their SMILES. SMILES is a way to represent this as a single text file.
Is it also search by CES number?
Sorry? You can search by CES number. You can search by SMILES, but many people don't know what the SMILES, but some manufacturers do. You can search by that, you can smell by this, or by name.
And for CAS numbers, your database for chemicals that might have multiple CAS numbers?
Yeah, so for most compounds, the CAS number is unique, but there's some where it's not. Usually, for example, where it's sold as a mixture, like some petroleum mixtures, some oil mixtures, and then it's difficult for us to do that. So then it's better to search it by the name or by the SMILES if you're looking for one specific chemical. Mm-hmm. Right, and it provides you, see, for just very simple, this methylparaben has all these names. So people have come up with all sorts of names, and so it goes and looks for any one of those, commercial names and so on, and tries to get at that, because you may look at your bottle and say, it has propyl acetoform, and so then it would come up with this one here and give you the opportunity. It also identifies the chemical type, so we've sort of gone through and identified, and so we have different models for different types, so it can look at organic chemicals, ionic, non-ionic, nanomaterials, and so on. So we're going to add the chemical, and we could put a nickname if you wanted to just keep it simple. Sometimes the names are huge, so you can keep it down to, MP or whatever you want it to. So now we have our region, we have our chemical, and if it was part of formulation, that you could have different fractions. So that would allow you to enter, your formula with different fractions, and then the results would be weighted based on the fractions that it has. Right now, we didn't pick a formula. Then we can go to the chemical properties. So it goes and pulls information from databases, mostly EPA databases, but some of them are other tools that we use. It was mentioned Vega, EpiSuite, and Test are the tools. Yes. Mm-hmm. So it provides information on, for example, the molecular weight, the octanol air and octanol water partition coefficient, the density, and so on. So all the information that's needed for the fate and transfer calculation. Also pulls information from about transformations, the half-lives, that are predicted for the environment. And if we had several regions, we would see the different regions, and you could modify them. The user could modify them if they have specific information for a given region. So just okay. Yeah, I thought you had a question.
So from the parameters we were just looking, which ones are potentially regional specific?
So some of them are not. So many of these are not. Just a second. So we have also total wastewater removal at the treatment plant. Total removal from wastewater treatment plant. These could be region specific based on the typical level of wastewater treatment. Some regions have, for example, in the U.S., many are secondary and also tertiary. But in other parts of the world, it may not be. So you could modify this and make that. Or the amount that goes to one or the other removal by wastewater would be different, and the sludge may be different. So those could be the transformations. For example, some of the half-lives in aerosols and air may be different based on amount of sunlight they may have, or the number of days where they have, cloudy days. So and sometimes some of these in the water columns may be different based on the type of water chemistry. So if someone was really knowledgeable, could modify these values. Yeah.
Is there a way to know which of these values are modeled and experimental? I guess where they come from, the uncertainty.
When we do so all of this, when we do the properties, there is actually, we don't have it in here, but there is a way to get in your report at the end which ones were brought from experimental data and which ones were from model data. And we went very quickly through the screening information. That also provides you which tools were used. If it was estimated, which tools were used for that estimation. Because it's very important for you to know where are we getting our information, correct? Yeah. Yeah, sure. So here, for example, it has, these were estimated EpiSuite, these were experimental from test, these were experimental EpiSuite and test, and so on. So it provides you with that information. Okay. Then we can take a look at the human toxicity information. And here it doesn't find information, so we would have to enter the information for this chemical. And there's no cancer risk. And then we're going to skip, no, we can't skip it. We have to actually go through it because once we have it there, we have to do it. So it will provide, again, some values for these ecological toxicity. And by default, we put in 4 key organisms that are used a lot for ecotoxicity assessment. These were all estimated values, so it's shown here as estimated. The user could modify them if they have better information, and they can add additional species for freshwater sediments if they had information for that. Marine, if you go down to terrestrial, we always calculate for earthworms because there's a lot of data for them and can be estimated. So that's a useful set of organisms. And then we get to the chemical use. So now we're getting to the release part. This is the shampoo, so it'll be consumer use. And then this is how much of the chemical is used per year. And so here's where we have to go, and either we do the top down before and put it in there, or we do it from bottom up and put in a certain amount in terms of kilograms per person per year. Do you have a value there? You don't have it. You have it in your exercise? Yeah. So it's so many milligrams. Yeah. Good. We'll go to the spreadsheet later and show you how to do it. And then because we can define the chemical use by product category or functional use. So it's a product category. We know what the product is. It's shampoos. And so if we continue, then you can select the category. It's down in the care and scare. And then it could be down the drain, or it could be an aerosol, or some other. So that's why you have to sort of specify which ones it is. And so that tells it how it's going to go from being used into, is it going to the wastewater? Is it going to the indoor air? Even though we say down the drain, there could be, if the volatility is high enough, it could show some volatilization, and it could show that there'll be some indoor air. But this is the primary route depending on the properties. The two key properties are the vapor pressure and the solubility. Yes.
So when you select the route of down the drain, how do you apportion what fraction goes into the air?
It does it based on the vapor pressure and the solubility. It tells it that the primary route is going to be so that it knows that it's going to go that way. Because if it was an aerosol, then the route through the wastewater is going to be 0. So that's why we use that information to sort of say, okay, we want to have that this way or not. Mm-hmm. Mm-hmm. And then because right now we're going to say 100% is in these products, but it could be less. And then this is an indoor use. You could put a fraction for outdoor, but it's very small for shampoo. And then it provides you with the chemical release. So now it tells you how much is going. Because of the low volatility, very little goes into indoor air, a tiny amount goes into outdoor air, and then this is how much is going into freshwater systems already all the way out to our environment. Marine environments, none or almost none to these soils, only to soils that receive biosolids. A small fraction goes to landfill, and most of this compound will actually be biodegraded in the wastewater treatment plant. And it has to add up to 100. So you could, if you have better information, or if you want to see, what if it doesn't really go biodegraded? I want to put it more into some of these other ones. You could make changes, but it does require you to make sure that it adds up to 100 because we need to have a complete mass balance. So it wants to know, where are you putting this? If you take it from here, where are you putting it elsewhere? Yeah.
Again, the split between indoor and outdoor air,
yeah.
It shows 0 for indoor air.
Yeah, so it's because it's less than 0.001. There's enough ventilation that, it's assuming that it's going out. Yeah. Mm-hmm. If we had something that was more volatile, we'd see a number here. So we'll see that when we do the paint strippers. Mm-hmm. So that provided us with the release that will be, and so then it translates into kilograms per day. So we get an idea of where is it going to go in the environment in terms of kilograms per day, and that's what we need to then do the calculations. And then the other information that we need to have, is it a constant release, as I showed you yesterday? Is it the product that you're selling is already a constant? Or are your sales increasing and your production volume is increasing? Is it decreasing because of a phase out? Is it seasonal, or is there an accidental spill? So we provide with different release scenarios based on the information that you may have. Mm-hmm.
I see there is nothing in there, but in outdoor air, there are some in there. Which the source for the outdoor?
We can go. The sources from the indoor, there's enough that blows out that it goes into the outdoor air. So even though we assume that there was no release directly, there is some transfer from the indoor environment to the outdoor environment, and there's enough that you would see. Let's go back to chemical release. You would see next. So just go that one here. Tiny amounts. So your milligrams per day are going into the environment. So it's a very, very tiny amount per person.
Sometimes you can also beat the landfill too.
Yeah, it could be also released from landfill or others. Yes. Mm-hmm. Yes.
I just wanted to point out, please use the microphones when you're asking questions.
Okay.
Online, participants can't hear. I know we don't have microphones on every table, but if that one needs to be turned on, I think more participants can hear. Thank you.
Okay. Any other questions? So again, this is a tool that helps you to right up to here get an idea of the actual potential release in a particular region for this chemical. And basically the information that you needed was the chemical properties, which we provide you with. If you have better information that can be updated, we didn't right now use this, we'll use it for the risk assessment. And then the other input that was needed was the chemical use, how much is being used. And that's why I say that's a really critical value. And we have to go to these exposure handbooks. We have to go to information that maybe the manufacturer has or somebody else has as to what the actual chemical use. So this is probably the most critical piece of information that we need the user to provide to do the calculations. So a lot of changes on what you do with that chemical use. And that's why we talk about the top-down and bottom-up approach, just, different ways that we can get at what that may be. After we have that, then we go and do the chemical release. We do provide you with a spreadsheet. Later on, we'll take a look at it. We'll provide you with a spreadsheet that gives you all the values that were used in the calculation so you can actually review them, change them, and modify them as needed. But right now, we're sort of just going through and showing you how we go to get this information. Okay? Any questions? Okay. So let's go back to the spreadsheet, to the PowerPoint. So that gives you an idea of how we do release. Next, what we're going to look at is a couple of simple models. So we're going to now move into the exposure estimation. And I created two simple spreadsheets. One of them is indoor air, and the other one's dermal exposure. These are based on some of the topics that I presented yesterday as to how we look at, for example, a indoor environment. And with a steady state calculation, you can use a simple spreadsheet to get an idea about the indoor air concentrations and then translate those into exposure doses. So we're going to go now to those spreadsheets. First, the indoor air spreadsheet. So we have here in the spreadsheet, first, the most important thing is my disclaimer here. It's meant to be just for instructional purposes. I've checked it, we've rechecked it. We had a couple of little bugs in there. I think it's all correct in terms of the calculations, but review all assumptions for your own calculations. This is meant to be more for giving you an idea of what could be done, but it's for you to sort of make sure that the numbers that go in there are correct and that, you know, you have understood the assumptions for all of these. And we talk about product one, product two. You know, these could be any products. Right now, the information is for some of the chemicals that we looked at in terms of the paint stripper chemicals. And then we have here, for example, information that's needed. How much product is needed per application? And we gathered this from the exposure handbooks. We've played around a little bit with the numbers. So the numbers right now shown here may not directly reflect that, but it'd be easy to adapt them to the values that you may have. Again, we don't know exactly the percent of the formulation that is the chemical of concern, but again, just some values to sort of get us started. And then it converts it into milligrams. So this is how many milligrams are used of that chemical in product one and in product two for that application.
What assumptions do you make as far as product density?
Right now, we just went with a simple like density of the water. So one thing that this doesn't have is correcting for product density. In some of the other tools, we'll see concepts, but they do have that in there. But yeah, that's a good point. Mm-hmm. Then how much area is covered by the product? This is so assuming that you're painting or they're removing paint from 30 square feet, how much is the time needed? So what's going to be the exposure that someone may have if they're out there? The vapor pressure of the chemicals. Again, we got that from those websites. And then this calculates a rate of volatilization. So based on some information that we've collected in the laboratory, I have one of the lab exercises I have with my students is to actually see how fast things evaporate in a fume hood. Now that's a very specific environment. So this may not reflect actual volatilization rates in an open environment. But just gives you an idea of typical rates, so milligrams per hour that are reduced. And then also, you know, if you apply that much, actually you would actually volatilize all of it before the hour for this chemical is so volatile, whereas this one still will have quite a bit of residual left, so it doesn't volatilize a significant amount even within an hour and 25 minutes, an hour and a quarter. The other thing that's needed is to put this mass into a volume. We need to know the size of the room. And here we used a typical room, and I guess we've played around with the height. 8 feet is a little short, but 8, 15, and 15. So we can modify that, let's say, make to 10 feet. Doesn't change the results drastically, but it does change the volume somewhat. So again, you could say, what's the typical room they're going to be using this product? It could be that you think about several rooms, but usually this would be used in a room. And another important disclaimer from yesterday, these products with that high volatility and their issues should probably not be used indoors. So just, you know, this is an example, it's an exercise, but it gives you an idea how we would calculate it. And so what we've done here is to then take this and plot the predicted concentrations in indoor environment like this for the two products at different ventilation rates or ventilation ratios. So I is the ratio between the ventilation rate and the volume of the room. And so if you have basically closed all your doors, it would be the highest concentration, and as you increase the ventilation rate, concentrations decrease. It's not very significant, but it would affect the exposure doses. Yeah.
What's the significance of the negative in the original amount?
That is all volatilized completely. It's gone. Yeah. Mm-hmm. I just wanted to do a kind of a sanity check that, were we in the right order of magnitude? And this shows that basically, yeah, it does all go away. Yeah.
For study volatile based on how speed gas charges efficiently in butane to your online tool.
In indoor environments, I would have to double check. I believe so, but I would have to double check. Yeah. Mm-hmm. Because particles in indoor environments, I just was in a workshop a month ago, are a very poorly understood area in terms of, there's some people, but in terms of modeling and in terms of understanding how much are they resuspended and all that, there's not a lot of good information. We understand the processes, but we don't have a lot of solid information. So I'm trying to remember whether we have that or not. Just want to make sure. Right. The point is that many of these volatiles would stick to particles, aerosols in the atmosphere, in the indoor environment, and could settle down eventually. So that's why it's important to consider. Yeah. Mm-hmm. So then we take that information and then we can convert that with the equations that I showed yesterday into an inhalation dose as a function of ventilation ratio. So if you scroll down just a little bit, we can see what the dose would be in milligrams per kilogram per day using the spreadsheet. So just in the interest of time, is it clear what we've done here? We could play around with it. So we can go around and play around with some of these values. For example, we could change these, but it just gives you an idea of how one goes about doing the calculations. You have the information that comes from how the chemical is used, and then some of the minimal information about the properties, the room to do the calculation, and then does the calculations for the inhalation dose. Okay. For the shampoo products, their vapor pressure is much more similar to this, so the concentrations would be around down there for those. Now, not for the fragrances, just for these preservatives. Okay, any questions? So let's take a look at the Dermal one. So here we have the Dermal. So this is looking at dermal dose as a function of exposure frequency. We could have picked another parameter to look at, but exposure frequency, how much do people use shampoo, is something that may vary. I use shampoo every day. My wife uses it once a week or a little, maybe a little bit more, but roughly, a lot less. And so, different people will have different exposures to it based on that. So information that we need is, for example, the skin surface area. And again, if we go to the exposure factors handbook, it provides you what's the typical skin surface area for different parts of the body. Here, the idea is that probably you're exposed to most of your body. What's the typical exposure time in terms of hours per day? How long you're exposed. And yesterday I had a question about this value here. So for some compounds, the exposure duration is your entire lifetime. For other ones, this is, for example, for an adult, because we're looking at body weight of 70 kilograms. So it's only 60 years, but it could be you could look at it as a child and look at the exposure for a certain period of their life. If we're looking at a product that's used more in an office, it would only be, let's say, 40 years, the number of years that you spent in an office. Yeah, that's a little rough, right? And then this is the chemical concentration contacting the skin. So what we've done here is to look at what are this comes from looking at what are some of the types of the product, how much is applied per day. So for shampoos, about the mean is 16.4 grams per day of shampoo. Here we did use the density of the product, and then the active ingredient for three different, for the methylparaben and the other two, looking at some data, what would be typical values for the active ingredient. Pretty sure that should have been a 0.8, but yeah, it's okay. And then that gives you the amount applied per day. And then for our website, we use kilograms per day, so we convert it to a kilograms per year value, actually. Yeah.
For shampoos, actually, when you try to estimate, it's also important for us to consider what's the retention factor?
Yes.
Like skincare products, if you apply, 100% is assumed to stay on the skin. But when you actually use shampoos and conditioner, a lot of them actually wash it out.
Yeah.
So you have to actually consider
retention.
Yeah, retention factor.
Yeah,
for shampoos and conditioner.
Right.
Normal retention factor is only 1%.
Right.
But
so just to repeat it for people,
that creates about at least 100 different folds.
Yeah. So just to repeat it for the people who are online, one thing that would be needed to consider here is the amount of the retention of that product. So you applied a certain amount of product that included these different preservatives. How much is that retained? And the conservative assumption is 100%. But that would be the highest dose. And it's usually not the likely retention. So in some of these studies, you find information about what has been observed as the retention of that, and it may be 50%, 10%, much less. So
actually, they have done extensive
studies.
Yep.
For shampoos and conditioner in general, retention factor is like 1%. Skin care product is 100% in general.
Yeah. Right.
And like there are some other the other types of products, for example, you use semi-permanent hair dyes and other things, that's about 10%. So that is well-studied information that is already available as part of it.
Okay.
Yeah, that helps narrowing down the uncertainty factors and actually assessing it.
Correct. Right.
So how do we account for this?
So one would have to use some retention factors to reduce, for example, if you have this amount applied and the retention is only 1%, then multiply that down by,
Right.
And likewise, for certain other scenarios, you can, depending on how you define exposure time, and you can adjust exposure time and duration. If you're talking, for example, about something you use partially during the day, office environment, depending on, you can either adjust the exposure time.
Right. You can adjust the exposure time here, the exposure duration, things like that. Yeah. Right. I believe in my calculation, the retention is here in this value. So it's here. It's over here. Yeah.
I didn't see that.
Yeah. I think I'd have to go back and check, but it's a really good point that not everything's retained 100%, and sometimes it's a very small amount because you're actually exposed to it a very short time.
No, the insult you have small retention. Leave on almost 100%.
Yeah. Right. Was there another question?
Yeah. So it seems like this is more of like a de novo exposure calculation. Doesn't necessarily follow like a typical model like ConsExpo. Just curious as to how these sorts of calculations are going to be reviewed, because from what I understand, a lot of the exposure models have scenarios set up, which have a varying degree of expert input on uses and all those sorts of information.
Yeah.
Versus this, where you enter in that sort of information. If you could just talk about how that information will be considered upon review of a given.
Sure. So, of course, how it will be considered for review is not for me to say.
Sure.
What I can say is this was only meant for instructional purposes here. Okay. We'll take a look at ConsExpo next. And again, those tools have been reviewed quite a bit more extensively. This was just to sort of show and say, well, we could vary some of these parameter values. It's easy. Let's change the exposure duration down to 5 years, just for an example, and then you can see how that may change the actual dose. Okay. It doesn't have an effect because it's affected by the averaging time. So, these things, these two go hand in hand. And so that doesn't change that. So you can see which parameters change it. But that's a really good point that, these are tools. This is not meant to be the tool that you should be using necessarily for your calculation. It gives you a starting point just to see how these equations work out. I gave you this equation yesterday in the presentation. Right. So just wanted to sort of show how it works. But again, there are tools like ConsExpo that can be used. And if you have that, you should use it. Thanks. Sure. Any comments from the TSC on that? We're good. Okay. All right. So let's go over now to ConsExpo. And so that is this tool. And so it's a tool that's been developed by this institute in Europe. It's National Institute for Public Health and the Environment. And they basically have made this tool available for consumer exposure. You can look at different types of assessments. Right now we have it for different, the paint strippers and the shampoos, but you could start out and do one for many, many different consumer products. So it includes a lot of the exposure factors. These have been modified by them, so that's built, but this is something that you could use this tool to work with. So let's take a look at an example with the shampoo. Okay. So starts out, you identify your application and your substance, and then go ahead to the scenario. So here then you can decide whether you want to look at all exposures, inhalation, dermal, and oral. So one could choose all three. Again, we're talking about whether there's an exposure issue. So if you wanted to, you could actually look at that. You could then choose dermal and oral. And then you can provide your information, direct product contact, the amount of contact that you may have, the weight fraction of the substance, the total product amount, and also provides you with an ability to do the uncertainty analysis built into the tool. So we'll have a conversation a little later about that, but here you could modify the exposure area and have not just a single value, but a distribution of values. So it's a very powerful tool to be able to do that. And you could pick the type of distribution, uniform, normal, log normal, and so on, and then put in the values depending on how you choose that. So it's a very useful tool for doing these calculations. And then we can take a look at some of the outputs. So here, for example, and then gives us the exposure. I think that's it, because you didn't have anything that varies. No? Yeah. So it just provides you with the information for what's the exposure that you would have based on use of this particular product. It can also, graph it out, and for that you would have to sort of pick a variable that you want to sort of have as your independent variable. So you can take a look at that. Yeah.
How do these compare with the values from
We've checked them, so we made sure that they were fairly close. They're not exactly the same, but we checked them to make sure that they were. And initially we had a difference, not in this one, but the paint stripper example, and we figured out there was a bug in the calculation, my mistake. So, but yeah, so the idea is that they should be pretty close, right? Right. Okay. So again, this is another way for you to do these calculations. And then let's go to our website just to show you how we also take this information and look at the overall exposure. And we've already run some of these, so we'll take a look at the ones that we've run before. So we can show the various regions for, let's take the shampoo first. So this particular part of the calculation takes minutes. And since we're running a little bit out of time, we've already done that. We can take a look at the dermal exposure just to see the values that go in there. So it needs information about the density of the product. That's important to have that there. Exposure duration, exposure frequency, volume applied per event, and other information that's needed for the person using it. So we, again, populate this information, but if you know different, you can use that and consider that for your calculations. And again, we checked it, compared it against context to make sure that we're doing this calculation. So we can take a look at the results. And so first it's going to give us what are the risks. So we can take a look at the human risks. And if we click on cancer risk, it doesn't generate a figure because we did not provide a slope factor. So because there is no known cancer risk, we don't have a value, it cannot generate that. So we don't want to provide that. Here is the non-cancer risk. So for this particular product, there would be no significant non-cancer risk for any one of these outdoor or indoor or dermal ingestion based on the information that we provided in terms of the risk thresholds. And then the intake dose, this would be the intake dose. And not surprisingly, the biggest exposure would be dermal. And had we run the indoor, we did run it before, Catherine, and there we showed that it was very small, very, very tiny, so not a significant one. And then the predicted cancer. We can go back to the ecological risk. So in terms of ecological risk, first it gives you kind of a big picture screenshot, and everything green basically has a very low risk. So all of these do not present, for those organisms that we looked at, do not present a risk. The ones that are grayed out is because we have no data in terms of the organisms living in these environments, so we cannot predict it, but unlikely to be significant. And then we can show also if there's an exceedance, what would be the exceedance? But of course, because these are all below, we don't have anything exceeding it. Sometimes we'll see some of these go up, and we'll see it in the other example. They go up by the threshold that EPA has set for that. And then the exposure, so we can sort of get an idea of what would be the exposure concentrations. And so everything is below these thresholds. These are the toxicity thresholds for these organisms, this here. Everything is below by several orders of magnitude. So for this compound, which is methylparaben, we basically would not expect to see much. And what we do see is that the concentrations are, some of them, there's not a lot of variability. In others, there's a bit more variability. It depends on the size of the different compartments. This is fresh water. And we can see there are some differences across different regions, even orders of magnitude difference in some of them, but nothing really rises. In some other examples, we'll see that makes a difference in terms of the ecological or human risk. Any questions? Okay. And then let's go to the amount of fate. So this provides you the concentrations. Again, a snapshot of concentrations, so you have an idea of what would be the concentrations, where we see the higher concentrations, freshwater and freshwater sediments for this one. Everything else basically is going into soils. This tends to partition in that way, and so it goes more into the soils. And then the daily concentrations for, let's say, freshwater or biosolids soil. So freshwater, it'll give you the concentrations for the suspended sediments, freshwater, sediment water, and so as you can get an idea where the concentrations are going to be. Let's take a look at the methylene chloride example. So before we go that, we ran the three compounds. So let's take a look at compare them across. So that's the other part. So this actually compares the three compounds. Again, no cancer risk because we don't have that information. And all of them are very low in terms of their other risks, but the thresholds are different. In terms of the doses do vary. And here we actually see that for this phenoxyethanol, there is an indoor air dose. It's a little bit more significant, slightly more volatile. But for the other ones, it's very low. But it gives you an idea of what's the dose in milligrams per kilogram of body weight per day for the three different compounds based on the amounts that are typically used for them. And then their predicted concentrations. The most important would be the dermal. And then ecological risk. Again, from the information we have, none of these would present ecological risk. Okay. Any questions? Okay. So let's go to the paint strippers. So this is now for the paint strippers, and we're going to start out with looking at the risk, the human risk. So cancer risk. So this one is for the methylene chloride. And so here, that would show the cancer risk for this compound. So it's below the threshold that we have here for the conditions that we have. The highest one would be the indoor air, and there's a small contribution from outdoor air in some of these environments. So it does get out eventually to the environment, and those then would contribute slightly to the overall cancer risk. We could also provide what are the outdoor concentrations if you had them for this particular compound, and then that would be added in here. Right now we assume a background concentration of a certain amount. And then the non-cancer risk is here, so very low from a non-cancer risk. And these would be the intake doses, so it gives you the amount in terms of milligrams per kilogram per day for indoor air, outdoor air, and ingestion. So in Visalia, there would be some exposure through ingestion. There's exposure everywhere. It's just this one is noticeable. These are so tiny you can barely see them right there. Yeah, was that a question? Yeah.
How do you explain, for example, ingestion?
So if this compound gets out into the environment, and then it contaminates the waters and food in the area, and so eventually the assumption is that if you ingest that, then you would be exposed to some of those products. Mm-hmm. And you could take a look at whether you see that pathway as being relevant or not. So if you don't think that's relevant, you could modify that to, eliminate that pathway.
So that's because there's more agricultural activity?
Yes, there's a lot of agricultural activity, and it's a fairly small environment. Yeah.
Thank you.
Okay. And then the concentrations. So here we see that the concentrations, this is outdoor air. Again, we see differences, and this is plotted again on a log scale. So we do see some differences in the environment. So none of them rise to the point where they exceed this particular threshold from the slope factor, but there are differences. There are regional differences, and they can be not quite an order of magnitude, but significant. It depends again on their conditions, the population they have, how they're laid out in terms of their land distribution, the climate they have, and other factors. And then we can look at the other one. Just comparatively, we can take a look at benzyl alcohol. So we can look, there's no cancer risk for that. And there's, so no cancer risk, non-cancer risk is very low. The doses would be different. This one is one that gets much more into the environment because it's a lot more soluble. So that's why there's a higher ingestion risk for this one. So again, even though everything else being similar, there's indoor air, that would be your highest exposure, but the ingestion could be significant. And so you'd have to sort of think about that as another factor.
Just one question.
Yeah.
If you go a little more up the, so if you look at the indoor air and outdoor air, my question is that do you actually deflect the local habits and practice like San Francisco? People, they don't really have AC. So they leave the door open. Mm-hmm. So in that case, you'll have the
ventilation rate.
Yeah, indoor and indoor will be very much.
It would be different, and that's where right. So yeah, correct. So the question was, why do we see differences? We didn't adjust for that here, but you could adjust it in the environmental parameters, and then in the indoor air parameters. What is the ventilation rate for different locations? So, for example, here we tend to in San Francisco we tend to for air conditioning we open up the windows. Right. You can usually it's not worth it for you to use air conditioning, but in Miami they close their windows and turn on the AC, right? Yeah. So that would be very different what you may see there if you change that. And so you could use the tool to sort of see what is the effect of doing that. How would that change the situation?
Okay. Thank you.
Yep. And we can then do the comparative analysis, looking at the two, just to see when we go here. So this would give you the comparative cancer risk. And again, it's not only going to show a risk for the one where we do have a slope factor, so it shows that, and then a non-cancer risk. They're both below, but you see the difference in thresholds are quite significant. The intake doses gives you what are the intake doses. Right now, it's showing, if we scroll up again, it's for the particular region. So this is for Visalia, so we can put San Francisco, for example. It will show us that information for that region there. So it shows us, the cancer risk, it's sort of the dose for different compounds. And so you can compare them and see what are the main differences between those and then where the concentrations may be. And then let's go to the ecological risk. So it compares the two of them, and both turn out to be low risk in terms of ecological risk. We don't have a lot of information for benzyl alcohol, so that's why it shows no data there. And then let's go to the fate and transport, environmental fate. So the mean concentrations, this tends to have higher concentrations because it's a lot more water soluble, so and it remains there. And then the daily concentrations, we could see how those play out in fresh water, for example. So here are the concentrations, and so we can see what the differences are. Much more variability based every time there's a storm event. There's a lot more flushing in this one here. So we see that showing up. So again, this is perhaps a little bit too much detail for some of the calculations you have. So we provide the information kind of summarized and then more detail. And if you want to get even more detail, if you want to go and take a look at all the assumptions and everything, we can go back to projects. So we were looking at here. We're not going to download it now, but you could download a detailed report that has every single parameter that was used in all the calculations. And also you can export all the results and then plot them the way you want. So you have that information available for you if you needed it for any additional, want to graph this in a different way, you want to show the results in a different manner, it provides all of that. Okay. Yeah.
So, Click focuses.
You have a mic.
So Click focuses on the product use stage exposure rather than the other life cycle segments.
Correct.
Correct. Okay.
We can add in some release from the manufacturing side, but we focus a lot on the product use. So it really was meant to look at product use as opposed to the other life stages, yes. It also considers, of course, some of the end of life because it has the wastewater treatment, the incineration and releases that you may have there, as well as how much goes to landfill. So it's product use and the end of life. It doesn't really have tools for us to do the calculation for the manufacturing side. The other part that's difficult is we don't know where the chemical is being manufactured. And so if we assume that it's manufactured in San Francisco, that'd probably be wrong. We don't know, but it may not be. And so we didn't want to make assumptions about that. And that's why we stayed away from the manufacturing point. Yeah. Did you want to add something?
Yeah. So
just a second.
Thank you. So Click has many modules, one of which is shown by Arturo this morning. So the risk assessment part is more kind of chemical specific, more kind of use phase specific analysis. We do have some other modules, screening level analysis and lifecycle assessment modules. Especially lifecycle assessment modules, it really spans throughout the life cycle, but we are not able to do detailed risk assessment type of analysis because of the fact that many of them are estimates and they are based on some generic databases for which location-specific information is not available. So different modules have a different kind of strength. So depending on where are you using this tool, you may pick and choose or combine multiple results from this tool.
Thank you. You had a question?
In cases where you want to look at a particular chemical, not just from a singular class of products, but from a range of
products, yeah.
How would you go about doing?
So you can do that. So if we're going to go through the exercise of the, like say, the paint stripper. So when we choose when you're choosing the chemical use in that module, there's a way for you to choose different uses. So you could say, well, maybe it's a solvent. So a solvent would be used in paints. Mm-hmm. It would be used in paint strippers. It would be used in many other products. Mm-hmm. So you could choose a number of product categories and assign a fraction to each one of them. So let's say you are coming up with a new solvent. You could do that calculation, or you wanted to see how would be the effect, what would be the contribution, the additional contribution in this new use. So you could do that as well.
Okay. I have one add-on. It doesn't have to be actually during the use phase, because if you're interested in the production phase, and then you know the production emission, so you can enter those numbers into our chemical release part, and then the fit and transport and until the exposure part can also be calculated. Right. So you don't need to use our chemical use predictive information. You can just go from release to fit and transport.
And sorry, because we missed you with the microphone. So
you can help me reiterate.
No, just go ahead and very quickly summarize.
Just for the so my point is you don't have to be focused on the use phase. So if you are interested in the production phase, you can also use the risk assessment tool, but you just skip the previous steps. You don't use the chemical release. You don't use the chemical use, but you can manually enter the chemical release amount and then run the fit and transport and then to generate the exposure amount.
if you know it's being manufactured in a particular location, you could add that in if you wanted to look at that in that region. Yeah. Just very briefly, if you can go to the point where we have all the tutorial, all the information, the background information as to what are the supporting documents for the tool, so that people can see where that's at.
The methodology.
Yeah, the methodology. So one thing that, the reason why we haven't quite released that, we have a lot of documents that go and explain all of the methodology. So where are all the publications? Where are we getting our data? What are the main sources for all the information? And also provides all the methods that were used and citations that we have. So how do we do the calculations? Which are the various tools that we use for this? So the idea was to provide a one-stop. So we're not using tools necessarily that we've created. Many of them are tools that have been created by others, and we have access, permission to access their tools in a fast way, so that you don't have to go and dig for this information all over the place. I showed you where you could get that information, but the idea is to try to get you as fast as possible going in an assessment and get you some numbers that are useful for your initial screening. And then if that turns out to be requiring more information, you could then zoom down and make it much more accurate. Any questions? We are almost out of time. Okay, well, thank you very much.
Thank you.
So the advanced topic this afternoon, we'll talk about the use of proxy data to address the data gaps and uncertainty analysis to the extent that we can. We have a lot of materials which is available online, as you know. We may not be able to consume all those materials today, but we'll try as much as we can. But before we go there, I would like to briefly show the life cycle impacts part and also the chemical properties or screening level analysis part of click data, which can be used as proxy values in your report. So I would like to ask Munya to go online and show. So again, it's the same click.net website. By the way, the only reason why we haven't really publicly released this version is that we are still fixing. So there are two reasons. One is that we are still fixing small bugs. But also, believe it or not, every time you run this model, it incurs cost to us because it's very computationally costly and resource-intensive process. So that when you enter new data and new chemicals, then we run our QSAR models. We actually pay for the AWS Amazon Web Service in the back end. And if a few of you are accessing it, that's fine. But if there are thousands of you are accessing it, we will end up getting a big bill. And we do not really have the means to pay that as of yet. So we are very cautious about releasing this website. And this was funded by US EPA. It was $5 million funding. We were very grateful about that. It took us 5 years to develop this website. But unfortunately, the funding is ending very soon. So we are actually looking for potential ways in which we can sustain this website so that it can continue to service to the community. So, yes, please.
To that, who do you see as the market for this, or from not from a sales perspective, but from a user perspective? Who have you targeted for use? Because that sort of dictates complexity, output, right, those types of things.
Exactly. So the question is, who is the market of this type of website? We have a lot of interest by the industry group. So not only the manufacturers, but also users. And we have been working with DuPont, DuPont. Ecolab and DuPont for a long time. And Dow Chemical for a long time. And the American Cleaning Chemical Institute, Unilever, also, so diverse industry groups have been contributing to.
It sounds like it's a sort of a consumer product cleaning focus.
And also chemical manufacturers.
Yeah. Right, but those are products that are released into the environment in significant amounts. I mean, that's the intended use.
Right.
It goes down the drain.
Right.
Mm-hmm. Okay.
And also, we hope that the Click tool can serve the responsible entities to, submit their AA. For example, if you like to have, spot data check. So So for example, you come up with life cycle impact analysis result and you want to have a spot check. This can provide a value based on predictive tool, as I will show you very briefly. So this can be a kind of reference point. And to a certain extent, I also hope the regulators, if they would like to also check, the numbers that they have received, and they would like to see, whether this compare, how does this compare with the other values? This could serve. Nothing has been formally, agreed as of yet, but I mean, we hope that this can serve not only the business community, the manufacturers, but also users and regulators and the like. Yes.
Yeah, I think like going through what we did yesterday and today, I think for regulatory purposes, it could be valuable in trying to understand and prioritize.
Mm-hmm. That's great comment. Thank you. Yeah, I think so. So I would like to just add a new project here. What shall we do? So shall we do benzyl alcohol?
Yeah, we can do that.
We can do that. Yeah, let's do benzyl alcohol and methylene chloride and see what happens. So we have to enter new project name and and let's do the screening level analysis and screening level scorecard. Yep. And we create. And in the back end, what we'll do is to just create a new project, and then you have to add a chemical. Let's select benzyl alcohol. Benzyl, the CAS number?
Yeah.
Okay. Ooh, I thought that you remember a CAS number.
That's
wow.
Scary.
Yeah. Okay. Wow. Okay, and then we'll search the chemical synonym database and disambiguate this chemical, and you can add a chemical. Yeah. And let's add one more chemical. We go up and methylene chloride. You can just let's try to type this time just to make sure that it works. Methylene chloride. Yep. So it identified the chemical. We added a chemical.
And then we can show the nickname.
Yep.
They are the same chemical, but we can change the name
yep.
to the one.
We use methylene chloride, that's the name. And let's have a view. So this is a kind of a high-level summary of the chemical properties and life cycle impact and hazardous chemical impact. So this spectrum shows the spectrum of the cumulative energy demand of all the substances that we have in the database. And of course, this is not the total spectrum of all the chemicals that are available in the universe. However, it does at least provide, what is the range of the impact of the chemicals per kilogram. And methylene chloride, this is methylene chloride, or benzyl alcohol, or it's methylene chloride. So methylene chloride is a benzyl alcohol. Benzyl alcohol goes around here, which is relatively low. And as you kind of hover over your mouse, it shows, where are the other chemicals, so that you have a sense of relative location of the particular chemical that you are interested in. And acidification is
a linear scale or a log scale?
It is, I think, linear scale. Yeah, linear scale. That's a good question. And we have a model confidence because some of these results are generated. So all of the life cycle impact results are generated using machine learning techniques, using artificial neural network. And some of the chemicals that we are modeling may be outside the training data. In that case, our model confidence is low. Uncertainty is high. So we are showing the model confidence so that you may want to use this when you're reporting, for example, the level of uncertainty involved in the data sets. Acidification is also low. Eco-indicator, this is a kind of more composite index of environmental impact. It's also low. Climate change also low. Human health impact is interesting that it is outside the range. So we could not credibly tell you what is the human health impact of life cycle human health impact, not the particular chemical of this, because the data that we have, training data we have, did not allow us to confidently estimate the life cycle human health impact of this particular chemical. Ecosystem quality is the same. So in this case, this is kind of inconclusive for us. So let's go down.
But it does indicate that it's higher.
Let's see.
Is that what that arrow is?
So
it's not outside of the range at the low impact level.
Right. I think.
I'm sorry, what's the point?
So the point is that, well, the bars are, there are 3 bars. Oh, red. Yeah.
So, well, if the bar is on the right, that means it's higher than the height to training.
That was the question. So that's an indication that it's uncertain, but it's higher. It's certainly not lower.
Not the other side.
Okay, and you would have a yellow arrow on the left-hand side.
Exactly, yeah.
If it was outside the training data range, but lower, expected to be lower.
Very good.
All right,
yeah.
thank you.
Thank you for the clarification. Yep. Great. And then hazardous indicator. Let's look at this, and especially in comparison with the methylene chloride, because it shows aquatic ecotoxicity of low concern. This is not a life cycle impact. This is the characteristics of the particular chemical that we are analyzing. It says aquatic ecotoxicity low concern, is not known carcinogen, is not known mutagen, is not known development toxin, and is not known xenoestrogen estrogen receptor, but it does have skin sensitizer effect. And if we compare that with methylene chloride, if we go back, so life cycle environmental impacts, I would say that these are not very different. They are relatively low, and human health and ecosystem health impact, it is similarly on the outer bound, the higher level, higher end. If you go down there, however, there is a quite significant difference in hazard indicators. Aquatic ecotoxicity is a medium concern, and it is known carcinogen, known mutagen, and development toxin. So now we are, with the click tool, we just created a new project, and we have chosen life cycle impact module, life cycle assessment module. And let's look at the life cycle inventory estimates. And this time we can test some other chemical, like TDCPP that we played with. Like, let's try to just type TDCPP, whether it can search. The chemical synonym database is quite extensive, so you may be able to identify what TDCPP is. Sometimes it cannot, so we'll see. So when we do that, basically what it does is that it connects to the PubChem and the ChemSpider through APIs to retrieve this information. And I think it correctly identified what TDCPP is. So we add the chemical. Yeah. And it says incomplete. And if we click incomplete, the reason is that the chemical you selected was not found in our database. So it means that we could not pre-calculate this life cycle inventory for this chemical because we didn't have enough information. So in this case, there are some options you have. So if we say yes, then there are 2 options. One is to use proxy chemical. Let's see what happens if we use proxy chemical. So if we choose proxy chemical, then what it does is that it retrieves the chemical structural similarity module, and it searches the chemicals that are structurally similar, which also have life cycle inventory data in our database. It seems that trichloroethyl phosphate does have life cycle inventory database, and it has a high similarity. So this might be a good proxy value. If you go down there, there are some other chemicals with a lower similarities. So should we choose something on the lower and then go back, or? Okay, let's try. So if we choose one of them and run the models, then it retrieves the information based on the proxy values. We can go back, and we can choose the closest one. This might be the best choice. So we will retrieve the life cycle inventory information. So again, I don't think that you can complete an AA report based only on the click tool, but this can be one of the tools in your toolbox. In that way, I think that it can provide some useful information, especially when there's a data gap. Seems that it's taking quite some time. It's doing a lot of thinking. Yeah, but we have, okay, we go. So it shows lifecycle inventory data. So again, as we have done the exercise this morning, in order for us to understand their environmental impact, we need to characterize them. If we want to understand their trade-offs and our judgment on which one is better or worse, we need to probably normalize and weight them. So this is just one of the steps that one would need in order to understand their life cycle impacts of the chemicals. Okay, with that, yes.
That's the inventory for one chemical?
One chemical, yes. So as I said, generally life cycle inventory contains multi-thousand elementary flows.
But I'm seeing values of -12 there, so elementary.
Yeah, inputs.
You mean really low input?
Yeah, so the values are very low. So if there are some negative values, possibilities is that, sometimes they generate waste heat that can substitute, for example, production of heat using fossil fuel. In that case, it may have negative values. So there are many reasons why negative values you may be able to see. And if we click the methodology, we are working on a paper actually. So once this is published, you can use that as a reference, how these are calculated. So it will be peer reviewed so that you can reference it there. Okay, now let's go back to the slide. Yep. Okay. Great. Now we can go this. Okay, so the big question is what to do if we don't have data, which is often the case when we are dealing with life cycle impacts and also risk-related impacts. It's rarely the case that we have all the data, that we need out there. So AA guide very specifically tell us what to do in those situations. So we will talk about data gaps and data quality assessment, and if we are given time, then we can probably talk about qualitative and quantitative uncertainty analysis, and just briefly we can mention that. So first, data gaps and quality assessment. So AA guide says the responsible entity may use any of the variety of approaches to address data gaps. So it does allow responsible entities to use multiple approaches to address data gaps. And these approaches help responsible entity to identify relevant factors, support decision-making, and select future research efforts. So through the use of this proxy data or the approaches to data gaps, you may be able to find some future research directions, future data collection needs, etc. So there are two types of data gaps that are discussed in the AA guides. One is process-specific data gaps, process-related data gaps. So data gaps for a specific process, for a particular chemical or product combination, for example, lag of data on resource and materials consumption and emission discharge from the process. Another example is inadequate data for a particular region, time period, or technology. So, for example, you are buying a particular feedstock to produce your product from China, and the only data set that you have for that particular product is from Europe. Then what to do, for example? So these are the kind of questions related to process-specific data gaps. There are another category of data gaps that is discussed in the AA guide is chemical-specific data gaps. We'll come back to that later. So for the process-specific data gaps, use proxy data set or extrapolated data to provide reasonable estimates. So it's basically proxy data or extrapolation, interpolation, those kind of techniques. So it will be easier to actually looking at the methodology. There are multiple methodologies that are really precisely described in the AA guideline. So we will do some exercise on that. Methodology 1 is direct proxy. So if product A and product B are assumed to have equivalent function and similar characteristic, process emissions of B is equal to process emissions of product A. This could be the assumption. So you remember that in our click tool, we just have shown that, well, the TDCPP was not a variable, so that we used another chemical. In that case, this is the direct proxy method, basically. And method 2 is average proxy. So if product A is manufactured in region A, product B is manufactured in country B, and assuming process emissions of product B is equal to weighted average process emission of product A from 4 countries in region A according to production volume, C1 represent country 1, C2 is country 2, etc. Then you do the calculation based on weighted average. So volume of the country's production and the corresponding regional production of A and other regions, their shares and their products. So this might look a bit complicated, but when it comes to actual example, I think it might be much easier to understand what this really means. Third one is scale proxy. So if you have data for 85% of the weight of a component, and you didn't have the remaining 15% of the data, then in that case, you can assume that 85% of the product component represent the other 15%. So basically, you extrapolate the 100% of your products based on 85% of the product's components. So this is the third approach. There are more approaches, but probably it will be enough to look into these 3 approaches. Why don't we go to the Excel file, hands-on exercise on lifecycle assessment, and there is a third tab. You can go, yeah, sorry. Yep, this one, yep. If we go to the third tab, proxy method, method 1, direct proxy. So if you can enlarge a little bit, I can probably, yeah. So the method 1 is basically, in this particular case, let's say, what we are interested in is to understand the ecotoxicity of 1,3-butadiene. And we didn't have that information, but product A, which was 2-butene, and product B, propylene, they have similar structural characteristics as compared to 1,3-butadiene. If that's the case, then, well, the question is, would you go with, for example, product A as a proxy or product B, or a combination of them as an average, for example? This is the methodology method 1. Yeah? And then method 2, average proxy. These are the market share values, 30%, 20%, 10%, and we know that butadiene made in China, Germany, and Canada, and basically the input that we are receiving, we don't know exactly where it's manufactured. So in this case, we can use the market share as the weighting factor to come up with the energy consumption information of the butadiene that we are receiving, for example. This is basically what method 2 is talking about. Method 3, scaled proxy. So basically, my product is produced using these ingredients: PET pigments, plasticizer, fillers. And our objective here is to calculate the greenhouse gas emission, lifecycle greenhouse gas emissions of the PET bottle. In that case, we didn't know what is the upstream lifecycle environmental impact, the greenhouse gas emissions of fillers. In that case, we can use the remainder of the component as the proxy and extrapolate that to calculate 100% of my product's greenhouse gas emission impact. Yeah? So of course we can take some time to play with these numbers, and I think that you can, let me see what time, Until when do we have? 1:45. We have only 15 minutes. So I would like to just leave it there. And if you have time later, probably you can, do the calculation by yourself. If there is any question, then let me know. We're okay? Good. Then let's go back to the slide. Yeah. Great. Thank you. And the next question is chemical-specific data gaps. Data gaps for evaluation of hazard traits or potential exposure of chemicals, and in that case, we can use read-across and trend analysis, such as QSAR, to estimate predicted missing endpoints. And basically, Click tool is an example of using, for example, QSAR or using the similar chemicals based on their chemical structures. So first approach that AA guideline talks about is the read-across method. So it is a technique to predict toxicity information for one chemical by using toxicity information of another chemical based on their structural or functional similarity, structure or functional similarity. And it requires trained experts to group chemicals based on structural similarity, mechanistic, or analogous approach. So in our case, basically, we use the structural similarity module that calculate the chemical structural similarities of multiple chemicals, or you can make an expert judgment, whichever is preferred. So obviously, it is based on the assumption that similar compounds, in terms of their structures, have similar properties. And sometimes this is true, and sometimes it may not be true. But again, we are talking about data gaps. So if there is no other data, then probably we should think about what is the best available data rather than what is the ultimately correct information. So this is an example. In our Click tool, if we want to, for example, search 1,3-butadiene information, then, well, it locates similar chemicals. They say, well, these similarities are high across propylene, 2-butene, and acrylane. So it does look quite similar. These are the chemical structures. Another approach that AA discuss in the guideline is the trend analysis, and this is a technique of predicting toxicology by analyzing correlations between a hazard trait to some physical chemical properties, such as quantitative, structure, and activity relations. So we also provide that in our Click tool. So basically, the idea here is that the biological activity or the chemical properties are the function of chemical structure. And based on that, we can estimate the relationship between the biological activity and chemical properties on the chemical structures. And there are many different tools, as you know, developed there. They're out there. In our particular case, we use 3 different QSAR models that are available. They're out there. That includes VIGA, EpiSuite, and TEST. These are the 3. And we generate numbers based on the best available information from the 3 sets of QSAR tools that are out there. So how do we address chemical-specific data gaps? As we talked about, use measured data from suitable analog, or use approximations based on surrogate data or estimated data from computational models such as QSAR. So again, we're talking about the situation where the data is not available, and DTSC guide, AA guide allows multiple approaches to fill up those data gaps. So we have briefly reviewed that. Now we have about 5 minutes, and we may be able to enter the quantitative uncertainty analysis very briefly, unless there's any question. Any questions? No? Yes.
When you some of the tools that you mentioned when we're looking at structural similarities, they recognize optical isomer differences and all that?
Can you repeat again?
Do they recognize optical isomers like cis and trans and
I see.
or the placement of the functional group? You have a hydroxy group if it's a N group or if it's in the middle of a chain. Or
how do we calculate the structural similarities, basically? Yeah, whether we account for all those functional group similarities, all those. I think in principle, yes. But I don't know actually the details what we are using in terms of chemical similarity calculation. Do we know?
It's based on the SMILES similarity.
Okay.
So I think in SMILES you don't consider the left or right hand side, the mirror situation. But yes, functional group, yes, considered based on the SMILES structure. Yeah.
Yes.
Can I add on that comment? So when you actually talk about toxicological QSA programs, so there are two different types of QSAs. One is quantitative QSA programs. The other is qualitative QSA programs. So when you do like LD50, there are a lot of database already available. So what they're doing is they try to construct structures based on that structure, then the oral LD50 values. So they try to establish correlations among them. So that provides a quantitative information. And the other qualitative database that they're using in their Vega programs, what they're doing is they actually try to identify structural component that can cause its sensitization or development toxicity. So they make build a database. So they make expert to make an informed decision. But this structure should be considered as mutagen, or this structure component should be considered as carcinogen or development toxicant. So they, based on knowledge basis on the structural motive, they actually identify this as strong mutant or a potent mutant or moderate mutant and weak mutant in the sample, highly sensitizing or moderate sensitizing and weak sensitizing. So it's actually based on, for most of the qualitative QSA programs, that's based on structural motive. So it doesn't give information on isomeric structure or chiral structure, the structure of that. It's more like specific functionality.
So in that case, it would be useful to actually use multiple different approaches and see whether it kind of come with it.
If you use Vega programs for development toxicity, and if you use the EPH test programs, you might see sometimes discrepancy.
Contrasting results.
Right. So that's why you actually need to look at use both programs, and actually they give information on what is their basis of saying this is mutagen or development toxin. Actually, they give out structural similarity, whether it's 90% or 80% or 50%, and also they provide a structure the component that has database, and you look at your chemicals and look at their reference chemicals, and you look at the relevance, whether your chemical is relevant to that chemical. So that actually you can pull out more information from actually reviewing the report.
Gotcha.
Yeah.
Thank you. So then, the only part that I would like to cover for the remaining 5 minutes is the steps that AA Guide recommends for uncertainty analysis. That is in your handout. So in your handout, the one-pager handout that is distributed today has recommended approach to uncertainty analysis in AA report. So it has step 1 to step 7. So step 7, and then there's a final step. So it looks quite complicated, but it's quite actually very detailed description of how we want to approach the uncertainty analysis. The first step is collect data from primary and secondary sources And then step 2, apply read-across, QSAR model, or proxy data to address some data gaps. And then step 3, so these are the linear steps. The step 3, make assumptions based on BPJ to address remaining gaps. And then step 4, create a list of information uncertainties. And from step 5, undertake a qualitative assessment of uncertainties first. And if they affect AA results, then, well, we need to do additional relevant factors needed to be considered. We need to assess additional relevant factors. And if additional relevant factors do play a role there, then return to the relevant factors analysis. We need to do iteratively. If not, then we can go directly to the preparation of AA. And there is another question. If it is no, still are there data, historical or BPJ, etc., to determine variation scenarios? If that's yes, then, well, another question needs to be asked. Would an uncertainty analysis significantly improve decision making? If that's the yes, then there is a step 6, which is undertake simple form of uncertainty analysis, such as sensitivity analysis or scenario analysis. If it is not, then you can directly go back to the preparation of AA report. So we will go to the next slide later, but so far the general principle here is that we'll collect data and first do the inexpensive qualitative analysis and see whether the uncertainty analysis will affect my conclusion. If it does, then we need to do more in-depth analysis and collect additional data. If not, then we can just conclude based on the information that is available. So AA guide to my reading is kind of trying to minimize the burden as much as possible based on the assessment that you perform the analysis when only is necessary and relevant. And then after step 6, so step 6 here, undertake a simple form of uncertainty analysis such as sensitivity analysis or scenario analysis. And then again, we ask the same question: do uncertainties affect AA result? And after after undertaking this sensitivity analysis, you found that, well, my result is very sensitive to some of the assumptions that we have made. In that case, we have to ask another question: is there information to refine the uncertainties? So based on the sensitivity analysis, we conclude that we cannot really make a meaningful conclusion out of this. In that case, we need to collect additional information. So would an uncertainty analysis significantly improve the decision making? If this yes, then step 7, undertake more complex form of uncertainty analysis. Again, we do more in-depth, more complex analysis whenever we determine that is needed. So it's not necessarily we directly go to the most comprehensive uncertainty analysis, but we try to do a simpler form of uncertainty analysis as much as we can, unless the more complex form is necessary. The final step is to present the uncertainty in the report based on this analysis. Yep. Any questions so far on these steps? So these are all the steps that we have talked about. And AA guideline allows a number of different ways in which we express uncertainties. So the simplest form might be to use plus, which means that, well, it could be an overestimate, a significant overestimation, or minus. If we don't know, you can do plus / minus, meaning that, well, it can be significantly, significant variation may be observed for that particular data point. You can also use pedigree type of approach, which I will briefly touch upon in the next session, which is based on the qualitative characteristics of the data, including reliability, completeness, temporal correlation, geographical correlation, and other technological correlation, and their respective scores. And these are the narratives that helps you to determine where your data point is located in these criteria. So there's what's called the pedigree method. We can also use this approach to more kind of semi-quantitatively or semi-qualitatively determine the uncertainties involved in the particular data set that you're using. So again, uncertainty analysis and the treatment of data gaps, there are various different approaches that are available. And in a sense, there is no scientific way to estimate unknown unknowns. That's not possible, basically. So still, I think the AA guide, describe multiple different approaches so that the responsible entities can try out, different approaches with the flexibility at hand. We do a lot of uncertainty analysis with the Monte Carlo simulation and large-scale sensitivity analysis, global sensitivity analysis, methodologies, etc. We still find that the uncertainty of uncertainty analysis itself is very high. So even if we do the uncertainty analysis, we may not be sure about the resulting conclusion out of that. So again, this is the area that much more development and refinement in science needed going forward. Okay, so that's pretty much what I prepared for the advanced topics. Any questions or comments on this topic? Nope. Looks like it's a very challenging topic, as it should be. Yeah. Okay, in that case, yes.
Is the assumption then that you would have some kind of assessment of every piece of data?
These are recommended steps, and I think that at least to my understanding, this level is necessary. So at this level, step 5, I'm pointing out step 5. So based on your qualitative assessment of uncertainties, if the uncertainties will not affect your conclusion in your AA report, then you're stopping right there. No further steps need to be taken. But if uncertainties are playing a role in your AA report, yes, I think that you should go forward. Again, this kind of judgment, I believe, is needed only for the material difference. So not all the information that you have collected need to go through this, only when they make material difference. Yeah. Any other questions? Yes.
So if person that have no experience on assessment, previous experience, how do they know whether they actually factored in that uncertainties into the estimation? Is there any references they can actually utilize to review whether appropriate uncertainty has been actually incorporated into the program and calculation?
Into the calculation, yeah. Right. So when you are referring to a number from a literature or, let's say, a website, and if they don't provide any further information on the variability or underlying uncertainty of that number, then the only way that we can understand better on the underlying uncertainty of that particular number is to dig more into and find out how the number is generated. And we should make an expert judgment about how complete and uncertain this value is. There's no other way, unfortunately, to go about it. So in terms of the qualitative uncertainty analysis, a lot of it, to my understanding, is expert judgment. In our case, in our tool, we provide quantitative uncertainty analysis with distributions in the result. Our tool does that, but in many cases, we don't have the luxury of accessing distributions of all the numbers that we need for AA. So in that case, a lot of it, I think it has to do with expert judgment. Okay. All right. Great, thank you. And then we will have a short break, I believe. No break? No break? I'm constantly optimistic. Oh, this. Okay, in that case, we can go into the applications of uncertainty on sample substances. So we can go to the Excel spreadsheet. The hands-on exercise on life cycle assessment. And then the last tab is what it is. So, Dr. Kim's question was right on, because we will do a lot of expert judgment based on the collective brain power of this room on the uncertainties involved in the life cycle assessment part of our calculation. And we have another segment, I believe. Do we have? Right, that's what we're going to do until 2:30. So we have enough time. That's great. So what we will do today is to populate basically this table. So we have done life cycle inventory calculation, life cycle impact assessment calculation, these two, and we want to analyze the uncertainty of our life cycle assessment result. Yeah? So how do we want to do that? Because we didn't give you the variability or standard deviation or distribution of these numbers, right? So you don't have access to those numbers. Of course, if you have access to those numbers, then you can put them together into a more fancier analysis if necessary, like Monte Carlo simulation, but you're not given that information, that what to do in that case. So what we can do, even without those variability information, numerical quantitative variability information, is to look at how those data were generated. So if you look at, let me see whether this is here. Oh, here we go. So you see that if you scroll up, these are the numbers. These numbers represent particular data sources for a particular information that was presented in the A matrix, B matrix, or characterization factors, etc. And these are the descriptors. These are the explanation of this particular data source. So based on these descriptions, suppose that you have extracted this information based on the literature review and by just looking into the data source that you have extracted a particular number, and now based on this information, we want to determine the level of uncertainty involved in that particular data. So number one, what this number one means is that if you go to Life Cycle Impact Assessment tab, on the top with blue color, do you see that these are the numbers? Yeah. So number one is this column, methylene chloride intermediate exchanges. Yeah. So I described that the intermediate exchanges of methylene chloride is the data of raw material requirement. So the data of the raw material requirement was from a production report of methylene chloride in 2003. So one important thing that we want to extract out of this is the year. Yeah, 2003. We have to think of, well, 2003 methylene chloride production is that accurately representing today's methylene chloride production or not? So that is one of the questions that we want to ask ourselves. And then water, natural gas, and electricity consumption data were obtained from a peer-reviewed model. So again, this is not a measurement data, it's model data, right? Okay. These are the kind of things that we want to kind of capture out of this. So that was methylene chloride. And this is only one column here. One column here, okay? And then similarly, we have descriptors for second process, third process, etc. And there are descriptors for the characterization factors. So the problem that we have here is that the uncertainty of the entire intermediate, so uncertainty of the final result. So if we want to compare if we want to understand the uncertainty of the weighted results that we have calculated here, that is a combination of uncertainties in the intermediate exchanges, elementary flows, characterization factors, normalization references, and weighting factors, right? Yeah. So as we take more steps, the result will become more uncertain. So we need to understand what are the uncertainties involved in each of these elements in order for us to be able to have an idea, informed idea on the overall uncertainty of the end result. So again, that's very challenging. It's very challenging, but we will nevertheless at least try to do this. So in the next, let's say, 10 minutes, we will, mute ourselves and we will kind of have some discussions. You can discuss with your neighbors. I can also walk around and try to kind of formulate the uncertainty levels of this A matrix, B matrix, C, and W matrices, and come up with an idea and have some discussion on what do we really think is the overall uncertainty in the result. Yeah? Shall we do that? Great. Then, well, for the next 10 minutes, I will just, let you read through and discuss with your neighbors, and then we will reconvene in 10 minutes. All right, let's go back to the reporting uncertainty tab and kind of have some discussion on overall uncertainty of, let's say, first say A matrix. What was your kind of general impression out of this exercise? Was it easy to? Very challenging.
Very difficult.
Very difficult.
And very difficult to be reproducible.
That's right. So if I do it, then I may have very different result than you do it, right? So this begs the question, to what extent the step 5 can result in a unanimous yes, unanimous no to finish your uncertainty analysis right there based on qualitative analysis. So, of course, it may vary depending on the situation, but I think that my personal view here is that I think that rarely step 5 will conclude you to finish up your AA report right there. It might be very challenging to get that conclusion right off from there. I think that some level of in-depth, more information, more uncertain analysis would be necessary. And I think that is also a good thing because when we generate the numbers, we often don't pay too much attention to the uncertainties behind those numbers. And I think this is an opportunity for us to really critically assess what are the variabilities, what are the underlying uncertainties, data gaps, and how they contribute to the conclusions that we are drawing. So what are some of the pitfalls that we can already kind of identify from this description? The first thing that I wanted to say here is that, well, the uncertainties involved in the number 1 to 9, they are all very different, right? So what was your judgment on, let's say, for example, item number 1? What was this table's judgment in terms of sign?
Sorry, I'm gonna pull it up.
Number 1.
What would we say, like -1?
-1.
But that's where we had like the model we said would overestimate, but we assumed production had gone down, so we thought that the older report might overestimate. Anyway, we thought that they might kind of balance each other out.
Gotcha. So in general, let's say newer technologies will be more efficient, right? So the older technologies may be, I think that, well, in terms of the energy consumption, for example, in the materials efficiency-wise, newer technologies are generally better. Mm-hmm. Yeah? So if I see that, well, it's a 2003 process, I would think that, well, this might be an overestimation, actually, rather than underestimation. Mm-hmm. Yeah. Yes.
I completely agree, but the magnitude issue, with the pluses, we realize that those are orders of magnitude. And so 2 orders of magnitude is huge.
That's huge, true, yeah.
And even an order of magnitude is a lot. That's 1,000%. Mm-hmm. So, it's hard to, I completely agree that the efficiency goes up both in terms of material management and energy expenditure, but does it go up 1,000%?
Does it deserve
right?
Minus,
does it
2 minuses,
right? Does it even deserve 1 plus or minus? It's hard to say that it's an order of magnitude difference.
That's a good point. Any thought on that?
We were actually debating if it should be 1 or 2 pluses because the range of sources there is not the same. Each one of them is different. So I don't know how you can weigh what the contribution of each one of those different 1 through 9, I believe.
Yeah. I mean, to be honest, I mean, I don't have a clear answer to all this, and I very much agree with all of you. It will be quite challenging. So, in being in lifecycle assessment field, uncertainty has been always the question, lingering question to us, and many researchers try to come up with a more qualitative, streamlined approach for uncertainty analysis. I have yet to see convincing qualitative uncertainty analysis so far. So I think that I don't have all the solutions to the questions that I'm bringing to the table, but I think at least what I can acknowledge is that it could be quite challenging. Yeah.
Does it make sense to put in a step where there's a sensitivity analysis, which is obviously a higher order of complexity, but and you said, that's within the realm of possibility, but if you do a sensitivity analysis first, you can focus your uncertainty analysis on the pieces of data that are most relevant, instead of having to go from A to Z in terms of trying to qualitatively assign relevance when you really don't have a very good idea at all. If you had an indication of you got your answer, but it's driven primarily by these 3 pieces of data or these 5 pieces of data, you could then focus your uncertainty assessment on those key pieces of data.
What do you think? What do you think on the comments?
Yeah, it makes sense that you focus if you do that sensitivity analysis.
Yeah. This table, any thought on that comment? Yeah.
Sounds like common sense.
Yeah, I agree. Yeah. Yeah.
And it's on that sheet. I mean, it's on the flow diagram you
right.
have there, but it's step 6.
Yeah.
So I guess the discussion is, maybe it makes sense if you have that, if you have that available, to have some indication of uncertain sensitivity.
What I would think is that, well, after having gone through a few of these, this type of analysis, if you look at these data sources and try to assemble them together to come up with the level of uncertainties, and then decide whether it affects your AA result. At that point, without going any further, you could have decided, oh yes, it does matter, and we need to collect additional data. And then you may have go right to this level already. So I don't think that you have to go through all the underlying data to come up with a conclusion there, and then move on to the step 6. And actually, I think that after assessing a number of key data points, if you think that, well, yes, we have to actually do some sensitivity analysis for major data elements, I think that is wiser approach to go step 6 and do some sensitivity analysis right there. Yeah. Yes.
However, if we were to go ahead with what we were doing, if you're looking, for example, at methylene chloride, the matrix A, and you have 9 different sources for the data, if you were to qualitatively assign a magnitude and direction, would you base that on the highest, most uncertain of the sources, or are you going to try and?
That's a very good question. Yeah, the question is, what we should base our uncertainty judgment on the data should be when there are multiple data sources. So that's where the contribution analysis comes handy. And that is actually what I wanted to discuss a little bit today. So although we have 9 different sources and with various different uncertainties involved, end result depends on fewer parameters. So off top of our head, we don't know that, right? So that's where the sensitivity analysis can play a role. So once we understand those contributions to the final result, then we understand what are the data sources that really matter. So I wanted to show you the spreadsheet, which we didn't do so we didn't have the time to do the contribution analysis. But if we do the contribution analysis, which I think I put it probably here. Here you go. So what I just did here is that, well, I put the X value, which is the total amount of inputs needed to produce 1 unit of methylene chloride, and multiply this one to the entire matrix. So what I did is if you look at the equation here, basically, in order to produce 1 kilograms of methylene chloride, we know how much of environmental emissions it will generate, and multiply that one to this B matrix, and it will come up with this. And then, well, 0.6 kilogram of the second product, which is chloroethane, and then we know how much of this water will be used. We have all this information, and because we have the characterization factor as well, we know which process contribute how much exactly. At the characterized result, we can do that. We can do the elementary flow level. We can do the weighted impact level. All that we can do all that. So based on that, generally 80% of the impacts are contributed by less than 20% of the inputs. So majority of the meaningful uncertainty in your result will be governed by small subset of the data that you will be using. So if you are to refine your data, you'd better focus on those major contributors rather than looking into the A to Z, first to the last data sources. So that's why I think the little more in-depth analysis and understanding the sensitivity of the input parameters to your end result will be very, very helpful, saving your time. Any other points that you'd like to?
Can you go back to that, the data, the spreadsheet you were just showing there?
Yeah, sure. Was it this one? Yes.
So just qualitatively, help us understand what we're looking at there. What contributed most? The 1.34? Across the top, or?
Yeah, so this result is based on the elementary flow. If we want to focus on the characterized result, we can multiply certain characterization factors to this. So let's say if we look at, so the majority of the difference in our result, let me see. So in our result, global warming didn't really contribute. As the human health was the major contributor because the normalized result was high and the weighting factor was high, right? In that case, let's look at the characterization factors for human health, which we have over here. So here we go. So let's look at the human health row. Well, actually, this is one chemical, only one chemical that is contributing, right? Yeah. So that chemical, let's look at this matrix that we have just generated. It is here. So that chemical, where is that chemical? Yeah. This one.
Yeah.
Yeah. This one is coming right from this particular, battery is not. This process, which is, I should have copied and pasted the labels too, which is, I think this one, right? Water consumption. Consuming water somehow generated the amount of emissions. So in that case, for the human health, the overall weighted result is pretty much governed by this one particular data source, which is number 7. Then, well, let's look at the description of number 7. natural gas electricity consumption data were based on expert judgment. Very uncertain in that case. Yeah. So this is the kind of ways in which we can kind of reduce the number of data that you have to investigate in terms of their uncertainty by looking at the major contributors. And you can do that at the elementary flow level, characterized results level, or weighted impact level. Again, I mean, I'm not necessarily be able to give you all the answers to the uncertainty analysis. It's indeed very challenging, but at least we had an opportunity to think together and discuss, our thoughts on the uncertainty analysis with you. So that's pretty much what we have prepared. If there's any questions on this or any other parts for now. Okay. Great, thanks. So the question is, when the data source is expert judgment, is it expected that one would provide references or rationale? That's a good question. So I have seen personal communication as a reference. And obviously, the quality of that expert judgment depends very much on the quality of the expert that the judgment is coming from. And then I think that rationale wise, I mean, unless there is a written document on the expert judgment, it may not be possible to really use the rationale as the basis of the quality. But I would say that in the medical field, I don't know whether you looked at some of the medical interventions are classified based on the evidences, and based on the evidences, meaning if there is a drug trial that has happened and show that this intervention works based on randomized controlled trial, that it has the high score. And the lowest score is expert judgment. So I would say that, well, as compared to other levels of evidences like modeled result or the measurement result, I would put expert judgment as the lowest. Of course, however, there are really good experts out there too. So I don't know how to really, come up with a blanket answer to that. So, yeah.
How about the directionality of the uncertainty associated with it?
That's a good question. That's a good question. I don't think that there is a clear directionality, whether, experts are always overestimating or always underestimating. It's difficult to judge, and especially if the experts are unbiased to that field, and I don't think that there is a clear directionality. But one thing that I would like to mention is that as a modeler, often I feel that, well, we who generate those numbers become more confident on the numbers that we generate sometimes. Whenever we come up with the numbers, we tend to underestimate potential uncertainties associated with it, and we may have missed something, we have completely omitted something, and those kind of possibilities are always there. So I think it's always good to think about having a third party or third person to look at the procedures and underlying data to assess the uncertainties if possible. Yeah. There's another question coming up. Okay, so the question is, sorry, can you explain that again? So I don't know what is that here, but previously you looked at water consumption. Water consumption. Oh yeah, so water consumption was the water consumption process. So water consumption process, it was this one, right? Mm-hmm. So water consumption process generated the environmental emissions that is associated with, this is methylene chloride emissions, that was the sole cause of the human health impact of methylene chloride. Yeah, so it was that context, so that we then now have to look at what is the uncertainty associated with the process number 7, and let's say process number 7. where is the natural? So process number 7 consumes natural gas and electricity. Oh, here we go. So these are the input parameters, but it seems that, well, so I kind of misspoke before, because so the expert judgment, here we say that, well, the number 7 natural gas and electric consumption data were based on expert judgment. That applies only to, these two cells, natural gas and electricity. So it seems that the emission of methylene chloride from water consumption process is not based on expert judgment. Yeah. So in that case, well, probably it's less uncertain than we should have given the score for the expert judgment. Yeah.
Isn't the calculation that we did it based on the matrix A?
Yeah, but these are the direct emission from water consumption, and the natural gas and electricity consumption by model data will be indirect impacts to water consumption. So all the emissions are directly generated by water consumption process, which is not based on expert judgment. Yeah. The finer details. All right. Any other questions? Nope.
Online.
Okay.
Because the weighting factors
are
so subjective,
would
the uncertainty usually be either direction?
Uncertainty for the based on the weighting can go either direction. Yes. So because of the fact that weighting is relative to different impact categories. So if we are overestimating the importance of one impact, that also means that you're underestimating relatively the importance of other impact categories. So it can go either direction. Yeah.
But what we're doing, isn't it relative? Aren't we comparing here methylene chloride and benzyl alcohol? So to the extent that we are consistent in the directionality by judging the sources that were used, that's more important than anything.
I think so, yeah. I think you're right, yeah. Consistency of the underlying data that is commonly shared between the two, it will not give the directional difference between the two substances to be compared. Yeah, that's correct. Yeah. Okay. All right, then we are approaching the end of the 2 days workshop. And originally we had, we didn't have any, we now have question and answer session. So probably I would like to ask my colleague Arturo Keller come up to the stage, and now we are opening the floor to you for any questions regardless of whether it was discussed today or yesterday or morning session or afternoon session. Okay.
Anything online?
No. I think what we can also do is, if there are questions that we didn't address today or yesterday, please feel free to email us, and we'll try to get back to you as soon as possible. So I think that's probably the best way to handle any questions that you come up as you're going forward and begin to use some of these skills and begin to dig in. I think that would be the best way to do it. So.
Yeah, this is more of a discussion than a direct question, but and I know you're the academic side of this and not the regulatory side, but can you talk a little bit about how the tools you presented, how you see them integrating into the regulatory framework? And because there's always that interface between the regulatory expectations, which are pulled together in one context, and then there's a clearly separate context where the academics and others put together the technical tools, and then obviously they need to interact at some level. But interested, and I acknowledge that you're not the regulator, so I won't hold you to any answers, but what is your perspective on how these tools will interact, or what role they will play in your understanding of the alternative analysis process specific to safer consumer products?
True. So this is just my view. I think, Arturo, you can share also your view. So we are grateful that part of the design process that we went through for Click project was supported by DTSC, so that we wanted to design the Click tool in such a way that it can help the responsible entities to generate some numbers and approximations based on our tools. So although it is not completely aligned, with AA, at least some of the data requirements, some of the numbers that you will need, responsible entities will need for generating AA report can be sourced, hopefully, from the Click tool. So obviously, more integration would be great if we have more resources to be able to provide that kind of service. We would love to, provide that service. And not only us, I think that there are other tools out there, I think, that can be further redesigned in such a way that it can support the responsible entities and make the AA report production easier and more convenient. I think there are more work to be done, but I think that the way how we try to design our Click tool, I believe that it addresses at least some part of the requirement by AA, and we're very, very proud of that.
Yeah, I think what we tried to do in our presentations yesterday and today was also to give you there's a number of tools out there. Ours is just one tool, and we hope that it will be a useful one that people will be using for AA and now AA. But it's not the only one. We discussed several other ones. We've done some benchmarking to see where we are, and we're still in that process. But I think it will be a useful tool for filling a lot of some of the gaps, and also some of the ways how you connect indoor, outdoor, things like that. That would be very important. So yeah.
Yeah, and I'll just add on from the regulatory view, is that good question, Bob, and thank you. I think what it highlights is that, and what Arturo and Sang-Won have highlighted for us are some tools and some approaches and ways to think about going through this process. And there's a lot of other ways you could do it as well. So it really highlights that when it comes down to on the regulatory side, there's going to have to be a dialogue that between the responsible entity and the department when we're talking about, a specific AA and a specific approach. The devil's going to be in the details, and there are a variety of ways to do it, many of which are reasonable and maybe some more than others. I think it also speaks to our hope is that by making the process one that has somewhat a lot of flexibility in it. For example, we allow responsible entities to collaborate and coordinate with each other so that you might, for example, bring one industry sector together and say, based on what we all know and what's all common ground, might we talk to the department about an approach for these segments of the process that we might all agree on, and then everyone can take their own piece of the process that's unique to their company or perspective. So, of course, acknowledging all that, the great opportunities that come with flexibility, it also creates uncertainty and sometimes a lack of clarity of a step-by-step cookbook process to how you get through the regulatory process. And we know that that's a balance, but I would just, again, stress that that's going to further make the importance of the dialogue in the process really important so that we're all on the same page.
I would like to just take on Carl's point that this is kind of creating a dialogue. I think I like that phrase. I think it's just, the same goes true for the Click tool too. So while you are using Click tool for your regulatory purposes or other purposes, if you feel that, well, why don't you guys design your tool this way or that way? You guys have overlooked this type of functionality. You should be able to, provide this type of information rather than that type of information. We'd love to hear from you. And we would love to, think about, serving the community better using our tool. We have a lot of resources in the making of the Click tool, and we hope that we can refine that further to serve the community better. Cool.
There's another online question.
But it's maybe more for Carl.
Oh.
Is there any plans to build a AA guide web tool that can incorporate those different data tools to help streamline the process.
An AA guide, what?
Web tool, like.
The web-based.
Oh, okay.
Yeah.
Well, the AA guide, if you haven't read it, please do. It's a few pages of really good stuff. It's by design meant to be amended and updated, and we look at that broadly as that's just one resource. Today's information is another resource. Earlier in the spring, we did a webinar on one approach to monetizing environmental impacts for air. It's going to be this combination of tools, examples, and things. We'll be talking at our Green Room and Science panel in September about some decision-making models. So the broad answer is yes, we hope to expand the amount of information that's available to people that will help people get through the process. Whether or not we ever have a web-based tool that you could like fill in the blanks and generate your AA, that would be a ways off, I think. And I think that the dangers with that are, I don't see in the near term a successful AA being done without that dialogue with the department, because from a regulatory standpoint, people are going to have a lot at stake. I'm looking at, let me see. So there needs to be some certainty in the decision-making process. And given the amount of flexibility, uncertainty, data gaps, and everything, coming up with a web-based tool that's going to generate your AA, I don't see that happening in the near term. That said, I do think that we might highlight certain tools and how they're useful, to what degree as they're developed. And as we start doing more, we'll learn more. So, and we hope to share that broadly. Any other questions? No. Okay. All right. Well, then, should we shift to the next phase, which is closing this out? Anyway, well, first, I just want to say thank you to a lot of folks. I want to say thank you to everyone online and all the students here today for participating. Back to the point of dialogue this is a new process. We're going to continue to learn as everyone is, and we really need to maintain that dialogue. But back to thanks. I want to thank Dr. Su and Dr. Keller and Mingyu for all the work they've done in support of this. I want to take a moment to thank our great AA team, specifically Melissa and Suzanne, Xiaoying, Valerie, Carrie, for making this happen today. It's not a trivial exercise. I also want to thank US EPA, who gave us our pollution prevention grant, and I'll call out John Katz's name to help us deliver this, and with the concept of getting information out there and building on it and continuing that dialogue. So a couple of thoughts. Meredith and I yesterday were reflecting on that this is sort of like that age-old question of how do you eat an elephant? And the answer is one bite at a time, right? And so we've seen some tools, we've seen some approaches. There are certainly other ones out there. We're going to hopefully build the community of practice in terms of alternatives analysis and alternatives assessment more broadly, because there's a lot of overlap. It's not just California's perspective, although if you're obviously regulated by us, that's the bottom line. But there's a lot of common ground out there and a lot of different other regulatory and non-regulatory aspects that is growing and building, and we're engaged with that community, and we're going to learn as everyone will. So it's important to keep in mind that this is not a simple process. It's a big process. I think I'm really proud of our staff who worked on the guide. I think it's an amazing thing, and I encourage you to read it. Maybe not all at once. And back to the dialogue, we need to know what your questions are and your concerns and your thoughts and your perspectives. So to that end, those people here can fill out the survey form, but Melissa will be sending out, it's already out? At the end, you'll be getting a survey, those of you online. We'd appreciate you taking a little bit of time to fill that out and give us some input. And even beyond that, as you have questions, as you have ideas and thoughts and concerns, please share that with our team, because that's how we're going to get better at doing this and make sure that this isn't just an academic exercise, but it's one that we can support and that people can get through successfully. So a couple of highlights looking down the road. In terms of things you should pay attention to. As I said, the Green Ribbon Science Panel will be convening on the 13th and 14th of September. Two of the elements on the agenda are very appropriate to this discussion we've had, those being talking about decision-making methodologies. Tim Malloy is going to help walk us through some of that, and we're going to have some further discussion. And we're also going to be discussing the department's look at, I think, 13 or so different AAs out there on the street that we evaluated through our lens. Yes, it's alternative assessments again. And recognizing that our criteria are different than the criteria that the practitioners did for those AAs. But what we're really trying to do is highlight some of the good work out there that we can point to and say, this is something you might use when you're looking at our process. So I think that'll be a really interesting exercise and hopefully helpful. And then just looking a little bit further down the road, the November 1st and 2nd will be the International AA Symposium held here in Sacramento, and it is the end of the week before the big CTAC meeting the following week, which I know many people will be attending. And again, that's going to be an effort that brings people from actually all over the world. We'll have people from Europe and across the country here to discuss some of these things about hazard and exposure assessment, about decision making, about how we use LCA and LCA thinking in this process. And again, the title of that symposium is Building the Field, right? And so this is something that's growing, and we're all learning. We really appreciate your engagement here today and yesterday, and we are counting on your continued engagement and looking forward to the road ahead. So with that, thank you very much again, and please fill out the survey and let us know if you have thoughts that you think we need to know. So thank you.